Welcome to the Deep Sleep Discoveries channel. There is nothing you need to remember, nothing you need to hold on to. This is simply a space to settle into, where thoughts can slow and attention can soften. Allow your breathing to become easy and unforced, like a tide that knows exactly when to rise and fall. Tonight, we are not rushing toward answers. We are drifting gently toward beginnings. The story of the universe often sounds loud when told quickly. Words like explosion and birth can feel abrupt, almost startling. But the deeper truth is quieter. The universe began not with noise, but with stillness giving way to motion. A slow unfolding, a gradual release of warmth and light into expanding space. As you listen, imagine traveling backward through time, past stars and galaxies, past planets and dust, toward a moment when everything was closer together, warmer, simpler. This journey is not about complexity. It is about easing back into origins where the rules of nature were fewer and the structures of reality were still forming. Let the mind loosen its grip on the present. Let the universe grow small, then smaller still. We begin not with an explosion, but with expansion itself. The Big Bang Theory does not describe an explosion in the way explosions usually happen. There was no central point blasting matter outward into empty space. Instead, the theory explains something quieter and more subtle: space itself expanding. Every region of the universe was once closer together, and over time the distances between all points have gently increased. This distinction matters because explosions move through space. The Big Bang did not move through anything. It created the very framework in which movement later became possible. Galaxies are not racing away from a single cosmic center. Rather, the space between galaxies is slowly stretching, carrying them apart without effort or resistance. An easy way to imagine this is through expansion rather than motion. As space grows, everything embedded within it naturally becomes farther apart. No edge forms. No center is left behind. From every location, the universe appears to be expanding uniformly. This idea replaces violence with continuity. Instead of a sudden blast, the universe experienced a smooth, persistent widening. That widening continues even now, quietly shaping the large-scale structure of everything that exists. Understanding the Big Bang this way allows the mind to relax. It reframes creation as a process rather than an event. And as space expands outward, we can ease forward with it, drifting naturally into the deeper timeline that follows. At its beginning, the universe was not large or empty. It was incredibly hot and densely packed, with energy and matter compressed into a state far beyond anything we encounter today. Temperatures were so high that familiar particles could not yet exist. Atoms, nuclei, and even protons were impossible under such intense conditions. In this early phase, energy dominated everything. Space was filled uniformly with heat, and differences from one region to another were almost non-existent. There were no stars, no planets, and no light traveling freely. The universe existed as a glowing, opaque sea where matter and energy were tightly intertwined. As expansion continued, this dense state began to cool. Cooling did not happen suddenly. It unfolded gradually, allowing new structures to emerge step by step. First came basic particles, then simple nuclei, and eventually the ingredients needed for atoms. Density and heat shaped every later feature of the cosmos. The smoothness of the early universe explains why large-scale structures appear evenly distributed today. Small variations present at the beginning were enough to guide the formation of galaxies much later. This early heat is not gone. It lingers faintly as background radiation, a soft echo of that dense beginning. And as the universe cooled, it created space not only for matter to form, but for complexity to arise, gently carrying us forward. According to the Big Bang theory, space and time did not exist before the universe began expanding. They emerged together, inseparable and intertwined. This means there is no meaningful sense of a moment before the Big Bang, because time itself was part of what came into being. This idea can feel unfamiliar because human intuition depends on before and after. Yet physics suggests that asking what happened before the Big Bang is like asking what lies north of the North Pole. The question assumes a direction that no longer applies. When space began expanding, time began flowing. Both were shaped by the same physical laws, unfolding together as the universe cooled and grew. Events could occur only once time existed, and locations could be defined only once space was present. This union of space and time forms what physicists call space-time, a single fabric that governs motion, gravity, and causality. Everything that has ever happened has occurred within this framework, including the formation of stars, galaxies, and eventually life. By understanding that time itself has an origin, the universe feels more finite, more intimate. The endless past dissolves into a gentle beginning, and as space-time stretches onward, it carries all moments with it, including this quiet one, as we continue drifting deeper into the universe's unfolding story. The Big Bang did not occur at a specific point in space. There is no single location where the universe began, no marked spot that can be identified as the center. Instead, every part of space was involved equally. The expansion happened everywhere at once. From any galaxy, the universe appears to be expanding outward in all directions. This does not mean that galaxy holds a special position. The same observation would be made from any other location. Expansion has no preferred place, only a shared history. This happens because space itself is what expanded. When space grows, all distances increase together. No region remains fixed while others move away. The early universe was smaller, not because matter was crowded into a corner, but because the entire fabric of space was more compact. Understanding this removes the idea of cosmic centrality. The universe does not revolve around a place. It unfolds uniformly, without hierarchy or focus. This equality is one of its most calming features. There is no edge rushing outward, no core left behind, just continuous expansion everywhere and always. As space stretches, it gently carries galaxies along with it, including the one we call home. And with that realization, the universe begins to feel less directional, more like a quiet field through which we are softly drifting. The expansion that began with the Big Bang has never stopped. Even now, space continues to stretch, increasing the distances between galaxies across the universe. This process is slow and subtle on human scales, but over cosmic time, it shapes everything we observe. Galaxies are not actively moving through space to escape one another. Instead, the space between them is growing, gently and persistently. On small scales, gravity holds stars, planets, and galaxies together. But across vast distances, expansion quietly dominates. Careful observations show that distant galaxies are receding faster than closer ones. This pattern reveals that expansion is uniform, not directional. It is the same process that began billions of years ago, still unfolding without interruption. Even more quietly, expansion appears to be accelerating. An unknown influence called dark energy seems to be driving space to stretch faster over time. Its nature remains uncertain, but its effects are measurable and consistent. This ongoing expansion reminds us that the universe is not static, it is not finished. It continues to change moment by moment on scales far beyond perception. And as space expands outward, it carries the present away from the past, creating room for the next chapter to emerge, gently guiding us toward the facts that follow. In everyday life, every event has something that comes before it. Morning follows night. Causes precede effects. But the Big Bang challenges this familiar structure. According to our best physical theories, time itself began with the expansion of the universe. Without time, the concept of before loses its meaning. This does not mean the universe appeared from nothing in a dramatic instant. It means that the framework allowing moments to exist came into being alongside space. Asking what happened before the Big Bang assumes time was already flowing, when in fact time was part of what emerged. Physicists describe this boundary as a limit of current understanding rather than a definitive answer. The equations guiding cosmic expansion stop working when traced back to the earliest moments. This breakdown does not imply chaos, only that new physics may be needed to describe that state. For the mind, this idea can feel unsettling at first, yet it also removes urgency. There is no missing chapter hidden just out of reach. The universe's story begins where time itself begins. As expansion carried the universe forward, moments unfolded naturally, one after another. And with time now flowing steadily, the universe could begin its long process of cooling, shaping, and becoming what we observe today. The phrase Big Bang did not begin as a careful scientific label. It was coined in the late 1940s by astronomer Fred Hoyle, who favoured a different model of the universe. During a radio broadcast, he used the term casually, intending it to sound dismissive rather than descriptive. At the time, Hoyle supported the steady-state theory, which proposed that the universe had no beginning and always existed in roughly the same form. To him, the idea of a sudden beginning seemed implausible. The phrase Big Bang was meant to emphasize what he saw as an overly dramatic proposal. Yet the name endured. It was memorable, vivid, and easy to repeat. Over time, as evidence accumulated in favor of cosmic expansion and early heat, the term lost its critical edge. What began as skepticism became shorthand for the dominant cosmological model. Ironically, the name itself reinforces misconceptions. It suggests noise, force, and explosion. In reality, the process it describes is quiet, mathematical, and gradual. Space expanding evenly does not resemble a bang in any conventional sense. Still, the name remains, reminding us that scientific understanding evolves not only through data, but through language. As we move forward, we leave the label behind and return our focus to the universe itself, continuing its calm and steady unfolding. When astronomers say the universe is expanding, they do not mean expansion is happening from a single origin outward. Expansion occurs everywhere simultaneously. Every region of space is stretching, regardless of location, scale, or direction. This means that from any galaxy, all other distant galaxies appear to be moving away. The effect is uniform, not centered. No place holds a privileged position. The laws governing expansion apply equally across the cosmos. This property arises because space itself is dynamic. It can grow, curve, and evolve according to physical laws. As space stretches, distances increase naturally without requiring objects to move through space in the usual sense. On smaller scales, gravity counteracts expansion. Galaxies remain intact, solar systems remain stable, atoms remain bound. Expansion becomes noticeable only across immense distances, where gravity weakens and space quietly asserts itself. This everywhere-at-once growth gives the universe a gentle symmetry. There is no leading edge, no trailing past. Every moment participates equally in the same process. Understanding this allows expansion to feel less dramatic and more continuous. It is not something happening elsewhere, it is happening here as well, though too subtly to feel. And as space continues to stretch uniformly, it sets the stage for understanding how motion itself is measured within an expanding cosmos. Although galaxies appear to be moving away from one another, they are not flying through space like debris from an explosion. Their separation increases because the space between them is expanding. This distinction is subtle but essential. In ordinary motion, objects move through a fixed background. In cosmic expansion, the background itself changes. Space grows, carrying galaxies along without requiring propulsion or force. From the perspective of any one galaxy, others recede because the distances connecting them stretch. This explains why galaxies can appear to move faster than light at great distances. They are not breaking physical speed limits. No object locally outruns light. Instead, expansion increases separation faster than light could traverse it, without violating relativity. Within galaxies, gravity dominates. Stars orbit normally. Light travels as expected. Expansion does not disrupt these structures. It acts only across the vast gaps between clusters. This understanding replaces motion with geometry. The universe changes shape rather than scattering matter. Expansion becomes a property of space itself, not of objects racing through it. As we accept this quieter view, the cosmos feels less chaotic. Galaxies drift apart gently, not violently, and this calm separation leads naturally to the deeper realization that space itself is an active participant in the universe's story, shaping everything that follows. Because the universe expands everywhere at once, it has no edge and no center. There is no boundary where expansion stops, and no point from which it began spreading outward. Every location participates equally in the same process. This can be difficult to visualize, because human experience is shaped by finite objects, but the universe is not expanding into something else. It is not growing into empty surroundings. Expansion is an internal change, a stretching of space itself. No matter where an observer is located, the view looks similar on large scales. Distant galaxies recede. The cosmic background appears uniform. This consistency confirms the absence of a central origin. The lack of an edge also means the universe does not have a detectable boundary. Traveling far enough does not lead to a cosmic wall or outer surface. Instead, space continues smoothly, possibly infinitely, governed by the same laws throughout. This structure gives the universe a sense of balance. No place is more important than another. No moment is privileged over the rest. Everything exists within the same expanding fabric. As the universe continues to stretch, it does so without destination or endpoint, just ongoing change. And within that change, we can settle into the idea that the cosmos is not rushing toward an edge, but quietly opening outward, carrying us toward the deeper physics still waiting ahead. One of the clearest signs that the universe is expanding comes from light itself. When astronomers observe distant galaxies, they notice that the light arriving from them is shifted toward longer wavelengths. This effect is known as redshift because visible light moves toward the red end of the spectrum as its wavelength stretches. Redshift occurs because expanding space stretches light as it travels. The farther that light has moved through space, the more it has been stretched along the way. This makes distant galaxies appear redder than they would if space were static. Importantly, this shift does not come from the galaxies emitting red light initially. It happens during the journey, as space gradually expands between the source and the observer. Redshift therefore becomes a record of how much expansion has occurred since the light was released. By measuring redshift, astronomers can determine relative distances and reconstruct the universe's growth over time. Greater redshift corresponds to greater distance and deeper cosmic history. This quiet stretching of light carries information across billions of years. Photons become gentle messengers, tracing the universe's expansion without sound or force. And as light continues its journey through ever-growing space, it prepares us to understand the patterns that link distance, motion, and time in the expanding cosmos. In the early 20th century, astronomer Edwin Hubble made observations that transformed our understanding of the universe. By studying distant galaxies, he noticed a clear relationship between their distance and the redshift of their light. The farther away a galaxy appeared, the faster it seemed to be receding. This pattern revealed that the universe was not static. Instead, it was expanding uniformly in all directions. Hubble's work provided the first strong observational support for the idea that the universe was once smaller and denser than it is today. Before this discovery, many scientists believed the universe was eternal and unchanging. Hubble's measurements quietly overturned that assumption. Without dramatic announcements, his data reshaped cosmology at its foundation. The expansion Hubble observed did not imply motion from a central point. It indicated that space itself was stretching, a realization that took time to fully absorb. Over decades, improved instruments refined his measurements, but the core conclusion remained intact. Today, Hubble's legacy extends beyond a single discovery. His work opened the door to modern cosmology, allowing scientists to trace the universe backward toward its earliest moments. As observations grew more precise, expansion became not just a curiosity, but a guiding principle. And with expansion established, scientists could begin exploring how fast it occurs and what that speed reveals about the universe's age and structure. Hubble's observations led to a simple but powerful relationship known as Hubble's law. It states that the farther a galaxy is from us, the faster it appears to be moving away. Distance and recessional speed are directly connected. This relationship does not depend on direction. Galaxies recede uniformly in all directions, reinforcing the idea that expansion is not centered anywhere. Hubble's law applies across the observable universe, creating a consistent pattern within cosmic motion. The law is expressed through a constant value, now called the Hubble constant. This number represents the rate at which space expands. Although its precise value is still being refined, its existence confirms that expansion is measurable and ongoing. By reversing this relationship mathematically, scientists can estimate how long expansion has been occurring. This allows cosmologists to calculate the approximate age of the universe, tracing it back toward its denser past. Hubble's law transforms expansion into something orderly and predictable. It shows that cosmic change follows structure rather than chaos. Every measurement adds clarity rather than confusion. As galaxies continue to separate, this relationship remains intact, guiding light across space and time. And through it, the universe quietly reveals not only how far it has grown, but how deeply its history is written into the motion of everything within it. If the universe is expanding today, then earlier in time it must have been smaller. Following expansion backward leads naturally to a denser, hotter past where matter and energy were packed more closely together. This logical reversal is one of the strongest foundations of the Big Bang theory. As distances shrink, temperatures rise. Energy becomes concentrated. Structures that exist today dissolve into simpler forms. Galaxies compress into clouds of particles. Atoms separate into nuclei and electrons. Eventually, even these distinctions disappear. This does not require assumptions beyond expansion itself. The same equations that describe growth forward in time describe compression when reversed. Expansion, therefore, carries with it a memory of its origin. Density shaped the universe's earliest behavior. High density meant frequent interactions between particles, allowing energy to redistribute rapidly. The universe behaved like a single connected system rather than isolated regions. As expansion continued, density decreased. Interactions became rarer. Structures could form without immediate disruption. The universe transitioned from simplicity toward complexity, guided by cooling and separation. Understanding this progression allows the mind to picture the past not as chaos, but as unity. Everything close together, everything sharing the same conditions. And as density relaxed, space opened gradually, creating room for variation, structure, and eventually the rich cosmic landscape that still expands gently today. In its earlier stages, the universe was filled with hot, charged particles that scattered light constantly. Photons could not travel freely. Any light that formed was immediately absorbed or deflected, making the universe opaque rather than transparent. This condition persisted for hundreds of thousands of years. Electrons moved freely, colliding with light and preventing it from escaping. The universe glowed intensely, but no clear images could exist. Light and matter were tightly coupled, locked together in a dense plasma. As expansion continued, cooling allowed electrons to bind with nuclei, forming neutral atoms. This moment, known as recombination, changed everything. Once atoms formed, light could finally travel uninterrupted through space. The universe became transparent for the first time. Photons released during this transition still exist today, stretched into microwave wavelengths by expansion. They form the cosmic microwave background, a quiet afterglow of this transformation. Opacity gave way to clarity, not abruptly, but gently. Light was freed, and the universe began to reveal itself. This transition marks a turning point between the unseen and the observable, and as the universe continued to expand and cool, this newly released light would carry information forward, allowing us to glimpse conditions from a time when the cosmos first opened its eyes. As the universe expanded, it did more than grow larger. It cooled. Expansion allowed energy to spread across increasing volumes of space, lowering temperature gradually and predictably. This cooling was not sudden or chaotic. It unfolded smoothly, guiding each new stage of cosmic development. In the earliest moments, temperatures were too high for particles to remain stable. Energy dominated completely. But as expansion progressed, conditions softened. Particles could persist longer. Interactions slowed. The universe began transitioning from pure energy toward matter. Cooling set the pace for everything that followed. Each drop in temperature allowed a new structure to emerge. First came elementary particles, then protons and neutrons, then atomic nuclei. Much later, atoms themselves could finally exist. This process resembles a slow release rather than a collapse. Heat did not vanish. It diluted, spreading outward as space grew. Even today, traces of that early warmth remain as faint background radiation filling the universe. Cooling also introduced time into structure. Events no longer happened everywhere at once. Differences could persist. Small variations could grow. Through cooling, the universe became capable of memory. Conditions from earlier moments influenced later ones, and as temperature continued to fall, the cosmos quietly prepared itself for light, structure, and the long era of formation that would follow. Before atoms could form, matter existed in a state known as plasma. In this condition, temperatures were so high that electrons could not bind to atomic nuclei. Instead, charged particles moved freely, creating an electrically active environment that filled all of space. This plasma was not rare or exotic in the early universe. It was the dominant form of matter. Protons, electrons, and light interacted constantly, scattering and exchanging energy. The universe behaved more like a glowing fluid than a collection of objects. Because electrons were unbound, light could not travel freely. Photons collided repeatedly with charged particles, preventing long-distance movement. This constant interaction kept the universe opaque and tightly coupled. Plasma conditions ensured uniformity. Energy spread rapidly, smoothing differences across space. This helped maintain the remarkable evenness observed in the cosmic background today. As expansion continued and temperatures fell, plasma slowly transitioned into neutral matter. This change did not require force, only patience. Cooling allowed electrons to settle into stable orbits, forming atoms for the first time. Plasma, once dominant, gradually faded into the background. Yet it remains an essential chapter in cosmic history. By shaping how light and matter interacted early on, plasma laid the groundwork for transparency, structure, and the universe's first clear view of itself. In the universe's early plasma-filled state, light existed but could not travel far. Photons were constantly absorbed and re-emitted by free electrons, bouncing endlessly without clear direction. Light was trapped within matter, unable to form images or carry information across space. This confinement meant the universe, though luminous, was visually inaccessible. There were no clear paths for light to follow. Every photon's journey was interrupted almost immediately after it began. Visibility, as we understand it, did not yet exist. This trapping maintained thermal balance. Energy exchanged rapidly between particles and light, keeping temperatures uniform. The universe remained smooth and connected, behaving like a single system rather than separate regions. As expansion lowered temperatures, this condition slowly changed. When electrons finally bonded with nuclei, photons were no longer scattered constantly. Light gained freedom of movement. The moment light was released marked a profound transition. For the first time, radiation could travel vast distances uninterrupted. The universe shifted from an opaque interior to a transparent one. Those freed photons still move through space today, stretched and cooled by expansion. They carry with them a quiet record of confinement, followed by release. This transition from trapped light to free light did not create noise or brilliance. It unfolded gently, allowing the universe to begin observing itself silently and continuously through the radiation that still surrounds us. Expansion did not prevent structure from forming, it enabled it. As the universe grew and cooled, conditions emerged that allowed matter to gather rather than disperse. Expansion reduced density enough for gravity to act locally without being overwhelmed by constant collisions. Tiny variations present in the early universe became important. Slightly denser regions exerted slightly stronger gravitational pull. Over time, these small differences amplified, drawing in surrounding matter. Without expansion, the universe would have remained too dense and chaotic for structure to persist. Without cooling, particles could not remain bound. Expansion balanced these forces, creating an environment where complexity could grow gradually. Matter began to clump into filaments and nodes. These patterns would later become the cosmic web, guiding the formation of galaxies and clusters. Structure emerged not in isolation, but through cooperative processes shaped by physics. This was not rapid construction. It took hundreds of millions of years. Patience was essential. Gravity worked quietly, steadily accumulating matter over immense timescales. Expansion continued alongside this process, stretching space while gravity shaped matter within it. These two forces did not compete, they complemented each other. Through this balance, the universe gained texture, uniformity gave way to pattern, and as structure slowly emerged, the cosmos prepared itself for the first stars, whose light would eventually illuminate the dark expanses expansion had created. One of the most important consequences of cosmic cooling was the formation of atoms. As temperatures dropped sufficiently, electrons could finally remain bound to atomic nuclei. This marked the universe's transition from plasma to neutral matter. Hydrogen atoms formed first, followed by helium. These simple elements dominated the early universe. Their formation reduced electrical interactions dramatically, allowing light to travel freely through space. This moment, called recombination, changed the universe's behavior. Matter and radiation separated. Photons began long journeys uninterrupted. The universe became transparent, revealing itself for the first time. Atoms introduced stability. Once electrons settled into defined orbits, matter could persist without constant disruption. Chemistry became possible, even if complex molecules would come much later. The creation of atoms did not involve sudden flashes or force. It unfolded gently across the cosmos as expansion continued cooling space uniformly. This transition also froze a snapshot of early conditions into the light released at that time. That light remains detectable today, carrying information from when atoms first formed. Atoms provided the building blocks for everything that followed. Stars, planets, and life all depend on this quiet turning point. As the universe cooled further, these atoms drifted through expanding space, gathering slowly under gravity, waiting for the next stage of cosmic evolution to begin. When atoms first formed and light was released, those photons did not disappear. They have been traveling ever since, moving through expanding space for billions of years. Today, that ancient light still fills the universe, though it has cooled and stretched into microwave wavelengths. This radiation is known as the cosmic microwave background. The cosmic microwave background, often called the CMB, is not coming from a single direction. It arrives uniformly from all around, bathing the universe in a faint, nearly even glow. This uniformity reflects the early universe's smooth conditions at the moment light became free. Originally, this radiation was far hotter, glowing brightly in visible and infrared wavelengths. As space expanded, those wavelengths stretched, cooling the light until it became microwave radiation detectable only with sensitive instruments. The CMB acts as a snapshot of the universe when it was about 380,000 years old. It preserves information about temperature, density, and structure from that early era. No other signal reaches us from such an early time so directly. This ancient light moves quietly, unnoticed by our senses, yet constantly present. It surrounds every galaxy, every star, every planet. As expansion continues, the CMB continues to cool, fading gently into the background. And in its soft persistence, it carries the universe's earliest visible memory forward into every moment that follows. The cosmic microwave background was not discovered through a targeted search. In 1965, engineers Arno Penzias and Robert Wilson were testing a radio antenna designed for satellite communication. No matter how carefully they adjusted their equipment, they detected a persistent background noise. This signal came from every direction equally. It did not change with time of day, season, or orientation. At first, they suspected interference. They cleaned the antenna, checked electronics, and even removed nesting pigeons, yet the noise remained. Unbeknownst to them, other scientists had already predicted the existence of leftover radiation from the early universe. When the two groups compared notes, it became clear that the mysterious signal was not noise at all. It was the cosmic microwave background. This accidental discovery provided powerful confirmation of the Big Bang theory. The radiation matched predictions in both temperature and uniformity. It could not be explained by stars, galaxies, or local sources. The discovery transformed cosmology almost overnight. What had once been theoretical became observable. This moment reminds us that the universe sometimes reveals itself quietly, without announcement. Ancient light waited patiently, filling space for billions of years, until technology was ready to listen. And once heard, it reshaped our understanding of cosmic beginnings forever. Measurements of the cosmic microwave background show an extraordinary level of uniformity. Across the entire sky, its temperature is nearly the same in every direction, differing by only tiny fractions of a degree. This remarkable consistency reflects the early universe's smooth, balanced state. Such uniformity suggests that distant regions were once in close contact. Energy could spread freely before expansion separated them. The universe behaved like a single connected system, sharing heat evenly across space. If expansion had occurred without this early connection, temperatures would vary widely. Instead, the near-perfect sameness of the CMB confirms that the universe began in a tightly coupled condition. This evenness is not absolute. Tiny temperature differences exist, measured in millionths of a degree. These small variations are critically important. They represent slight density differences present in the early universe. Without these subtle irregularities, gravity would have had nothing to amplify. The universe would remain smooth and empty. Structure depends on imperfection. The CMB therefore holds a balance between sameness and variation, uniform enough to reveal a shared origin, varied enough to allow complexity. As expansion stretches this radiation further, its temperature continues to decline slowly. Yet, its pattern remains frozen in time, preserving a calm and delicate imprint of the universe as it once was, evenly warmed and quietly waiting to grow. Within the cosmic microwave background's near-uniform glow are minute temperature variations. These fluctuations are extremely small, yet they carry immense significance. They represent regions where matter was slightly denser or slightly less dense than average. Over time, gravity amplified these tiny differences. Denser regions pulled in more matter, growing gradually stronger. Less dense regions became voids. From these early variations, the large-scale structure of the universe emerged. Every galaxy, cluster, and filament traces its origin back to these subtle imprints. Without them, gravity would have nothing to shape. The universe would expand smoothly, forever lacking structure. The fluctuations themselves likely originated from quantum effects in the earliest moments of expansion. Processes acting on unimaginably small scales left marks that later grew into vast cosmic patterns. This connection links the smallest scales of physics with the largest structures in existence. A quiet symmetry connects quantum uncertainty to galaxies spanning millions of light years. The fluctuations were not chaotic. Their distribution follows precise statistical patterns predicted by theory and confirmed by observation. This agreement strengthens confidence in our understanding of early conditions. As expansion continues, these structures evolve, but their seeds remain embedded in ancient light. The universe carries its earliest imperfections forward, gently shaping everything that has formed since. Despite its extreme conditions, the early universe was governed by the same fundamental physical laws we observe today. Gravity, electromagnetism, and quantum mechanics all played roles, though under energies far beyond everyday experience. What differed was not the laws themselves, but how they manifested. High temperatures caused forces to behave differently. Particles interacted constantly. Symmetries existed that later broke as cooling progressed. These early conditions simplified behavior in some ways. Matter was evenly distributed. Interactions were frequent and predictable. Large-scale irregularities had not yet developed. As the universe cooled, complexity emerged through gradual change rather than sudden shifts. Forces separated, particles gained mass, structures became possible. This continuity reassures us that the universe is not divided between an unknowable beginning and a comprehensible present. The same principles apply throughout, linking early moments to everything that followed. By studying relics like the cosmic microwave background, scientists test these laws under extreme conditions. Observations consistently confirm predictions, reinforcing confidence in the underlying framework. The early universe was not lawless or chaotic. It was orderly, constrained, and remarkably balanced. As expansion carried the cosmos forward, these same laws guided its evolution step by step. And with each cooling stage, the universe transitioned smoothly toward the richer, more complex reality that would eventually include stars, planets, and observers quietly tracing its origins. In the early universe, chemistry was extremely limited. Only the simplest elements existed, primarily hydrogen and helium, with tiny traces of lithium. Heavier elements such as carbon, oxygen, and iron had not yet formed. The universe lacked the complexity required for rich chemical interactions. This simplicity was a direct result of early conditions. Temperatures fell quickly after the Big Bang, allowing only light nuclei to form before expansion reduced density too much for further fusion. Big Bang nucleosynthesis ended within minutes, locking in this elemental composition. For hundreds of millions of years, these light elements drifted through space without stars, planets, or molecules. There were no solids, no liquids, and no chemistry resembling anything familiar. Matter existed as diffuse gas, shaped only by gravity and motion. This simplicity was not a limitation, but a foundation. Hydrogen and helium provided the raw material for the first stars. Inside those stars, heavier elements would later be forged through nuclear fusion. Every complex atom in your body began as hydrogen formed during this early era. Complexity emerged later, but simplicity came first. The chemically simple universe reminds us that richness does not appear instantly. It grows gradually, layered upon quiet beginnings. And as expansion continued, this simple matter waited patiently, gathering slowly, preparing for the moment when stars would ignite and chemistry would deepen. The formation of the universe's first atomic nuclei occurred during a brief but crucial period known as Big Bang nucleosynthesis. This process began just seconds after expansion started and ended within the first 20 minutes. In that short window, the universe's basic chemical composition was set. During this time, temperatures were high enough for nuclear reactions, but cooling happened rapidly. Protons and neutrons collided, forming hydrogen nuclei, helium nuclei, and small amounts of lithium. Heavier elements could not form because expansion reduced density too quickly. Once temperatures dropped below critical thresholds, nuclear fusion stopped. The universe moved on, carrying these early products forward unchanged. For billions of years, the relative proportions of hydrogen and helium remained nearly the same. This brief episode left a lasting imprint. Measurements of elemental abundances today match predictions from Big Bang nucleosynthesis with remarkable precision. This agreement strengthens confidence in the theory. The fact that such an important process occurred so quickly highlights the universe's efficiency. Fundamental outcomes were determined early without repetition or revision. After nuclear synthesis ended, the universe entered a long, quiet phase. Matter cooled, atoms later formed, and darkness prevailed. In this way, minutes shaped billions of years. A short, calm window determined the material from which stars, galaxies, and life itself would eventually arise, carried forward by the steady expansion of space. The Big Bang did not create the elements required for complex structures. Carbon, oxygen, nitrogen, and iron were absent at the beginning. These heavier elements formed much later, inside stars, through nuclear fusion. As gravity gathered hydrogen and helium into dense regions, the first stars ignited. Inside their cores, immense pressure and heat forced atomic nuclei together. Hydrogen fused into helium. Later, heavier nuclei formed through successive fusion stages. Massive stars produced elements up to iron. When such stars exhausted their fuel, they ended in violent supernova explosions. These events scattered newly formed elements into surrounding space. This material enriched future generations of stars and planets. Over time, galaxies became chemically diverse. Planets formed from dust containing elements forged in stellar interiors. Every atom heavier than helium in your body was created inside a star. The iron in your blood, the calcium in your bones, and the oxygen you breathe all trace back to stellar processes. This layered creation connects the universe's earliest simplicity with later complexity. The Big Bang set the stage. Stars carried the story forward. As expansion continued, space provided room for generations of stars to live and die. Through this ongoing cycle, the universe gradually transformed simple beginnings into rich chemistry, allowing structure, diversity, and eventually awareness to emerge within the vast, expanding cosmos. After atoms formed and light was released, the universe entered an extended era often called the Cosmic Dark Ages. During this time, there were no stars, no galaxies, and no new sources of visible light. Space was filled with neutral hydrogen gas drifting quietly under gravity's influence. Although the universe was transparent, it was also dark. The cosmic microwave background faded into infrared and microwave wavelengths, invisible to human eyes. No luminous objects yet existed to illuminate space. This darkness was not empty or inactive. Matter slowly gathered into denser regions. Gravity worked patiently, drawing gas into filaments and nodes. Small fluctuations began growing, guided by the patterns imprinted in ancient light. The Dark Ages lasted hundreds of millions of years. During this time, the universe prepared itself for the first stars. Conditions had to become just right. Density increased. Cooling continued. This long pause demonstrates the universe's unhurried nature. Creation does not rush. It waits. Within this darkness, the seeds of structure matured. Eventually, gravity overcame resistance and the first stars ignited, ending the Dark Ages and beginning a new chapter of illumination. As expansion stretched space outward, it also allowed time for this quiet preparation. And in the stillness of cosmic darkness, the universe gathered itself, ready to produce the light that would shape everything that followed. The formation of the first stars marked a turning point in cosmic history. These stars were unlike those seen today. They were massive, bright, and short-lived, formed from pristine hydrogen and helium without heavier elements. When gravity compressed gas sufficiently, nuclear fusion ignited in their cores. Light returned to the universe, ending the long darkness. These stars illuminated their surroundings and altered the behavior of matter around them. Their intense radiation ionized nearby hydrogen, changing the universe's chemical state once again. This process, called reionization, transformed neutral gas into plasma, allowing light to travel even more freely. The first stars lived quickly and died dramatically. Many ended as supernovae, dispersing heavy elements into space. This enrichment allowed later stars to form with greater stability and variety. These early stars acted as architects. They reshaped their environments, influenced galaxy formation, and established cycles of creation and destruction that continue today. Though long gone, their impact remains. Modern galaxies carry the imprint of their activity. Chemical diversity, structure, and light all trace back to their brief existence. As expansion continued, the universe grew more complex. With the first stars, simplicity gave way to richness. And with light restored, the cosmos began revealing its evolving structure, step by patient step, across the widening fabric of space. As the universe expanded and cooled, gravity became the quiet sculptor of structure. Regions with slightly more matter exerted slightly stronger gravitational pull. Over immense timescales, this gentle imbalance guided gas inward, allowing the first galaxies to begin forming. Gravity worked slowly. It did not rush or tear matter apart. It gathered. Hydrogen and helium drifted along invisible pathways, collecting where density was just high enough to hold them together. These growing concentrations became the earliest galactic seeds. Within these regions, gas compressed and cooled further. Star formation followed, feeding energy back into surrounding space. Young galaxies were irregular and dynamic, shaped by ongoing inflow and internal activity. Gravity did not act alone. Expansion continued to stretch space, preventing collapse on the largest scales. The universe balanced inward pull with outward growth, allowing structure to form without consuming everything. Over time, small galaxies merged into larger ones. This hierarchical growth built complexity gradually, layer by layer. Modern galaxies still carry signs of these ancient mergers. Gravity's work was never loud. It did not announce its presence. It simply persisted. Through this steady influence, the universe gained architecture. Vast collections of stars emerged from diffuse gas, guided by the same force that still governs motion today. And as galaxies formed, the universe's expanding canvas gained depth, pattern, and enduring structure. Galaxies did not form randomly throughout space. They emerged along a vast, interconnected structure known as the cosmic web. This web consists of filaments of matter stretching across the universe, intersecting at dense nodes where galaxies and clusters formed. The cosmic web grew from tiny fluctuations present in the early universe. Gravity amplified these differences, drawing matter into elongated strands. Between them, large voids formed containing relatively little matter. This structure resembles a three-dimensional network rather than a uniform fog. Galaxies trace these filaments, revealing patterns that span hundreds of millions of light-years. Even today, The distribution of galaxies reflects this early organization. The web's formation demonstrates how simple rules produce complex outcomes. Expansion set the scale. Gravity shaped the pattern. Together, they created structure without design or intention. Dark matter played a crucial role. Though invisible, it provided the scaffolding upon which ordinary matter collected. Gas followed dark matter's gravitational influence, settling into the same filaments. The cosmic web is not static. It continues evolving as expansion stretches space and gravity reshapes matter. Filaments thin, clusters grow, voids expand. Through this vast structure, the universe expresses order on the largest scales. And as galaxies continue drifting along these ancient pathways, they carry forward the imprint of early conditions, woven quietly into the expanding fabric of space itself. Not all matter in the universe interacts with light. Dark matter neither emits nor absorbs radiation, making it invisible to telescopes. Yet its gravitational influence is unmistakable, especially in the universe's earliest stages. Dark matter began clumping before ordinary matter could. Because it did not interact with radiation, it was free to respond to gravity earlier. This allowed dark matter to form the initial framework of structure. Ordinary matter followed. Gas fell into the gravitational wells created by dark matter, collecting where invisible mass had already gathered. Galaxies formed within these wells, shaped by dark matter's distribution. Without dark matter, structure formation would proceed far more slowly. Expansion would disperse matter before gravity could gather it effectively. Dark matter's presence allowed galaxies to form early enough to match observations. Though unseen, dark matter defines the universe's architecture. It influences galaxy rotation, cluster dynamics, and large-scale patterns. Its effects are consistent and measurable. The nature of dark matter remains unknown. It does not fit within familiar particle categories. Experiments continue searching for its identity. Still, its role in cosmic history is clear. Dark matter guided structure silently, without light or sound. And as expansion carried the universe forward, this invisible influence remained constant, shaping the visible cosmos from the shadows, allowing stars and galaxies to emerge where otherwise they might not. Transparency did not arrive all at once. The universe transitioned gradually from opacity to clarity through multiple stages. Each stage reflected changing conditions as expansion continued and temperatures fell. The first major shift occurred when atoms formed, allowing light to travel freely. Later, the appearance of the first stars reintroduced ionization locally. Their intense radiation altered surrounding gas, changing how light moved through space. This reionization spread unevenly. Pockets of ionized gas expanded outward from early stars and galaxies. Over time, these regions overlapped, gradually transforming the universe's overall state. Transparency increased step by step. Space became easier for light to traverse, allowing distant objects to become visible. This process shaped what modern telescopes can observe. Reionization marked the universe's second major phase transition. Matter changed state once again, guided by light rather than heat alone. These stages did not disrupt expansion. They unfolded within it, layered atop one another. The universe remained calm, even as its properties evolved. Understanding transparency as a process rather than a moment helps explain the universe's gradual complexity. Nothing changed abruptly. Each transition built upon the last. As clarity increased, the universe revealed more of itself, and through expanding space, light carried these revelations forward, enabling observation across vast distances and timescales, linking early structure to the cosmos we see today. Because light travels at a finite speed, there is a limit to how far we can see into space. When we observe distant objects, we see them as they were in the past. This means the observable universe has a finite age, shaped by both expansion and light's travel time. The oldest light we can detect comes from the cosmic microwave background. It marks the earliest visible moment, when the universe first became transparent. Anything earlier remains hidden behind opacity. As expansion continues, this horizon slowly grows. Light from increasingly distant regions reaches us over time. The observable universe expands not only in size, but in accessible history. This does not mean the universe itself is limited to what we see. It may extend far beyond observation. The observable boundary reflects physics, not edges. Time, light, and expansion together define our cosmic perspective. They shape what can be known directly. This finite visibility gives the universe a layered appearance. Each distance corresponds to a different era. Looking outward becomes a form of time travel, revealing earlier chapters. As telescopes improve, they push this boundary gently backward. Yet some moments remain unreachable. Within these limits, the universe offers a coherent story. Expansion sets the pace, light carries information, and within this expanding window, we quietly trace the universe's history, knowing that what we observe is only part of a much larger unfolding whole. In the early universe, matter and antimatter formed together in nearly equal amounts. Whenever particles of matter met their antimatter counterparts, they annihilated each other, converting mass into pure energy. This process happened continuously in the universe's earliest moments, yet a small imbalance existed. For reasons not fully understood, matter was produced in slightly greater quantities than antimatter. The difference was extremely small, perhaps only one extra particle per billion. But this tiny excess mattered. As annihilation continued, most matter and antimatter vanished together. What remained was that slight surplus of matter. From it, everything we observe today was built. If the balance had been perfectly equal, no matter would have survived. The universe would contain only radiation, expanding endlessly without stars, planets, or observers. The fact that anything exists at all depends on this asymmetry. Physicists call this imbalance baryon asymmetry. Its origin remains an open question, pointing toward physics beyond current models. This subtle difference shaped the universe quietly, without spectacle. A nearly perfect symmetry broke just enough to allow existence. As expansion carried the universe forward, that small excess of matter cooled, combined, and formed structure. And from a difference almost too small to notice, complexity emerged, filling expanding space with galaxies, light, and the conditions necessary for awareness to arise. In the universe's earliest moments, energy dominated everything. Temperatures were so high that energy continuously transformed into particles and back again. Matter and radiation existed in equilibrium, exchanging forms freely. As expansion continued, cooling reduced available energy. This shift allowed particles to persist longer. Energy condensed into mass following the relationship described by Einstein's equation relating mass and energy. This transition did not involve sudden creation. It followed predictable rules. As temperature fell below certain thresholds, specific particles became stable. Quarks combined into protons and neutrons. Later, these formed atomic nuclei. Cooling acted as a filter. Only particles light enough and stable enough remained abundant. Heavier, unstable particles decayed or annihilated quickly, leaving behind a simpler set of building blocks. This process shaped the universe's composition. The types of matter present today reflect conditions during these early cooling stages. Energy became structured, organized into enduring forms. Even now, this relationship continues. Energy and matter remain interchangeable under the right conditions. Stars convert mass into energy. Particles appear and disappear in high-energy environments. The early universe demonstrated this principle on a cosmic scale. As expansion softened extreme conditions, energy settled into matter, allowing persistence. And through this quiet transformation, the universe gained substance, giving form to the space that continued to stretch gently around it. At the highest energies of the early universe, the fundamental forces of nature behaved differently than they do today. Conditions were so extreme that forces now distinct may have been unified, acting as a single interaction. As the universe cooled, these forces separated in stages. Gravity likely became distinct first. Later, the electromagnetic and nuclear forces diverged. Each separation occurred as temperatures crossed specific thresholds. This process is known as symmetry breaking. Early on, the universe was more symmetrical, with fewer distinctions between forces. Cooling reduced symmetry, allowing specialized interactions to emerge. These transitions shaped how particles behave. They determined which interactions dominate at different scales. The familiar forces governing atoms, stars, and galaxies arose gradually from these early changes. Evidence for this unification appears in theoretical models and experimental results from particle physics. Although full unification remains unconfirmed, observations support the idea that forces converge at high energies. This layered emergence reinforces the universe's gradual nature. Nothing appeared fully formed. Complexity unfolded through cooling and separation. As expansion continued, forces settled into stable roles. Gravity shaped large-scale structure. Electromagnetism governed atoms. Nuclear forces powered stars. Understanding this history reveals continuity beneath diversity. The universe began with simplicity at extreme conditions. Through expansion and cooling, that simplicity unfolded into the varied interactions that quietly govern everything within the expanding cosmos today. Very early in its history, the universe experienced a brief period of extremely rapid expansion known as inflation. During this phase, space itself expanded faster than the speed of light. This did not violate physical laws, because nothing was moving through space faster than light. Space itself was stretching. Inflation occurred within a tiny fraction of a second after expansion began, yet its effects were immense. It smoothed out irregularities, flattened large-scale curvature, and expanded microscopic regions into vast cosmic scales. This rapid growth explains why distant regions of the universe appear so similar. Before inflation, they were close enough to share information. Inflation then carried them far apart, preserving uniform conditions. Inflation also amplified tiny quantum fluctuations. These fluctuations became the seeds of all later structure, linking the smallest scales of physics to the largest cosmic patterns. Though inflation is supported by evidence, its exact mechanism remains uncertain. Scientists continue studying how it began and ended. What matters is its outcome. Inflation set initial conditions that shaped everything that followed. Without it, the universe would appear far more irregular. After inflation ended, expansion slowed to a steadier pace. Space continued growing, but gently. Through this early burst, the universe gained balance and order. and as expansion settled into its long rhythm, the cosmos moved forward, carrying inflation's imprint quietly within its vast, expanding form. One of inflation's most important consequences is the universe's apparent geometric flatness. On large scales, space behaves as if it has no overall curvature. Parallel lines remain parallel. Geometry follows familiar rules. Without inflation, this flatness would require extremely precise initial conditions. Even slight deviations would grow over time. Inflation solves this problem naturally. During inflation, rapid expansion stretched any initial curvature, making space appear flatter, much like how a small curved surface looks flat when magnified. This process did not eliminate curvature entirely, but reduced it to near imperceptibility. Observations of the cosmic microwave background support this conclusion. Measurements show that the universe's geometry is very close to flat, consistent with inflationary predictions. Flatness influences how the universe evolves. It affects expansion, structure formation, and the universe's long-term fate. Understanding geometry provides insight into cosmic history and future behavior. This outcome reinforces inflation's role as a shaping process rather than a violent event. It adjusted conditions quietly, setting balance across vast scales. As expansion continues today, this flat geometry persists. Space stretches without curving back on itself or closing inward. Through inflation, the universe gained a calm, balanced structure. And within this nearly flat expanse, matter and light continue drifting apart, guided by the same gentle expansion that began at the universe's earliest moments. Before inflation, the universe may have contained uneven regions with varying densities and temperatures. Inflation acted as a powerful smoothing process, stretching space so rapidly that any initial irregularities were spread thin and softened. This created the remarkably uniform universe observed today. Without this smoothing, distant regions would appear wildly different. Temperatures would vary dramatically. Structures would lack coherence. Instead, the universe displays an extraordinary level of consistency across immense distances. Inflation did not erase all differences. It reduced them to small variations, just enough to allow structure later on. Uniformity and imperfection were balanced carefully. This smoothing explains why the cosmic microwave background appears nearly identical in every direction. Regions now separated by billions of light years share similar properties because inflation once brought them close together before carrying them apart. The process resembles gently stretching fabric. Wrinkles do not disappear completely, but they become subtle. Inflation stretched space in this way, calming early turbulence. After inflation ended, expansion slowed. The universe continued evolving, but now from a smooth baseline. This early smoothing allowed gravity to work predictably. It prevented chaos while preserving variation. Through inflation, the universe achieved coherence. It became a place where patterns could grow gradually rather than violently. And as expansion continued, this smooth foundation supported the emergence of structure, guiding matter and light through an orderly, expanding cosmos shaped by calm beginnings. While inflation smoothed large-scale irregularities, it also magnified the smallest ones. Tiny quantum fluctuations, normally confined to subatomic scales, were stretched to cosmic sizes during this brief expansion. These fluctuations became the seeds of galaxies and clusters. Quantum mechanics allows energy to vary slightly even in empty space. At the universe's earliest moments, these variations existed everywhere, fleeting and microscopic. Inflation transformed them into lasting imprints, As space expanded rapidly, these fluctuations were frozen into place. What began as uncertainty became structure. Slightly denser regions attracted more matter. Less dense regions became voids. This process links the smallest scales of physics to the largest structures in existence. Quantum behavior influenced the distribution of galaxies across billions of light years. Evidence for this connection appears in the cosmic microwave background. The pattern of tiny temperature variations matches predictions based on inflationary quantum fluctuations. This relationship reveals a deep unity in nature. The same rules governing particles also shape the universe. Inflation did not create structure directly. It prepared the conditions. It amplified possibility. As expansion slowed, gravity took over, building upon these amplified fluctuations. And from uncertainty stretched across space, the universe gained the framework for everything that would form later, quietly carrying quantum origins into its vast and expanding architecture. One of the most puzzling features of the universe is its large-scale uniformity. Regions separated by immense distances appear strikingly similar in temperature and structure. Inflation offers a natural explanation for this consistency. Before inflation, the universe was small enough for energy and information to spread evenly. Regions could interact, exchange heat, and reach equilibrium. Inflation then rapidly expanded space, separating these regions while preserving their shared properties. This process explains why the cosmic microwave background appears nearly identical in all directions. Without inflation, distant regions would never have been in contact, making such uniformity unlikely. Inflation resolves this issue without requiring fine-tuned initial conditions. It allows ordinary physical processes to operate early, then stretches their results across vast scales. Uniformity does not imply stagnation. Small variations remained, enabling structure to form later. Inflation balanced sameness and difference carefully. As expansion continued after inflation, these conditions remained imprinted. The universe evolved from a consistent starting point rather than a chaotic one. This explanation reinforces the universe's calm nature. Order emerged naturally from early interaction, followed by expansion. Through inflation, the universe became both unified and diverse. And within this balance, expansion carried uniform conditions forward, allowing complexity to develop gradually across the immense, quietly stretching fabric of space. Inflation provides a clear explanation for why the universe appears geometrically flat. Before inflation, space may have been curved in various ways. Rapid expansion stretched that curvature, making space appear nearly flat on observable scales. This flattening occurs naturally during inflation. Any initial curvature becomes diluted as space expands exponentially. Like zooming in on a curved surface, the local region appears flatter as scale increases. Without inflation, the universe's flatness would require extraordinarily precise initial conditions. Inflation removes that requirement, offering a simpler explanation grounded in physical processes. Measurements of the cosmic microwave background support this outcome. Observations show that space follows flat geometry with remarkable accuracy, aligning with inflationary predictions. Flatness influences how the universe evolves. It affects expansion rates, structure formation, and the universe's overall behavior. Understanding geometry provides insight into cosmic dynamics. Inflation's flattening effect did not eliminate curvature entirely. It reduced it to levels too small to detect with current observations. As expansion continues today, this flat geometry persists. Space stretches evenly without bending back on itself or closing inward. Through inflation, the universe gained balance at the largest scales, and within this nearly flat expanse, matter and light continue drifting apart, guided by the same calm expansion that began in the universe's earliest moments. Inflation did not last long. After a brief but dramatic expansion, it ended, transitioning the universe into a slower, steadier phase of growth. This ending, called reheating, converted the energy driving inflation into particles and radiation. Rather than a violent stop, inflation likely ended smoothly. Energy spread into space, raising temperatures and filling the universe with matter and light. This marked the beginning of the hot Big Bang phase more commonly described. Reheating reset conditions. It distributed energy evenly, restoring a hot, dense state across space. From this point, the universe evolved according to well-understood physical laws. This gentle ending preserved inflation's benefits while allowing normal expansion to resume. The universe remained smooth, flat, and filled with potential. Details of reheating remain uncertain. Scientists continue investigating how inflation ended and how energy transferred into particles. Yet evidence suggests a controlled transition rather than abrupt disruption. This calm conclusion fits the broader pattern of cosmic evolution. Major changes unfold without violence, guided by physics rather than force. As expansion slowed, the universe settled into its long-term rhythm. Inflation's role was complete, but its imprint remained. And within the space it shaped, the universe continued its quiet journey toward complexity, structure, and the vast, expanding cosmos we observe today. When inflation ended, the universe was left in a carefully prepared state. Space was smooth, but not perfectly uniform. Tiny variations remained, preserved across vast distances. These variations defined the initial conditions from which all later structure would grow. Inflation did not build galaxies directly. It shaped the environment in which gravity could work effectively. By stretching space and magnifying fluctuations, inflation ensured that matter would not collapse too quickly or disperse too evenly. These initial conditions were remarkably simple. They can be described statistically with just a few parameters. From this simplicity, complexity emerged gradually over billions of years. Observations of the cosmic microwave background confirm this picture. The distribution of temperature fluctuations matches predictions based on inflationary initial conditions with striking accuracy. Because inflation set these conditions so early, their influence extends across the entire observable universe. Galaxies forming billions of years apart share the same underlying pattern. This early preparation removed the need for fine-tuned beginnings. Structure arose naturally from generic physical processes. As expansion continued after inflation, gravity took over locally, building upon these initial conditions. Matter followed the paths inflation laid down. Through this quiet setup, the universe gained coherence. Inflation ended quickly, but the conditions it left behind still guide how matter gathers, how galaxies form, and how the expanding cosmos continues to organize itself today. Once inflation ended, the universe entered a new phase of expansion. Space continued to grow, but at a much slower and steadier rate. This change marked the transition from the inflationary era to the hot, radiation-dominated universe. During this period, energy existed mainly as radiation. Photons and relativistic particles filled space, interacting frequently. Expansion reduced their density and temperature gradually. Slower expansion allowed physical processes to unfold over time. Particles could collide, combine, and decay. Nuclear reactions occurred. The universe gained structure through patience rather than rapid change. This steady expansion followed predictable laws described by general relativity. The rate of growth depended on the universe's energy content, shifting as radiation gave way to matter dominance. As matter became more influential, expansion slowed further. Gravity began shaping structure more effectively, allowing small fluctuations to grow. This change in pace did not erase inflation's effects. It preserved them while allowing new processes to take over. The universe's rhythm became gentle and sustained. Expansion no longer overwhelmed everything else. It provided a stable backdrop against which matter could organize. As billions of years passed, this steady expansion carried the universe through multiple eras. And within this calmer growth, stars, galaxies, and complexity could gradually emerge across the widening fabric of space. For a significant time after inflation, radiation dominated the universe's energy content. Photons and other relativistic particles carried most of the energy, influencing how expansion proceeded. In this radiation-dominated era, energy density dropped rapidly as space expanded. Radiation thinned faster than matter because its energy was reduced both by spreading out and by wavelength stretching. This dominance affected structure formation. Gravity could not yet gather matter efficiently on large scales. Radiation pressure resisted collapse, keeping the universe relatively smooth. Despite this, important processes occurred. Particle interactions remained frequent. Nuclear reactions shaped elemental abundances. Conditions stayed hot enough to maintain equilibrium among particles. As expansion continued, temperatures fell. Radiation lost influence relative to matter. A gradual transition occurred, shifting the universe into a matter-dominated era. This handoff was not abrupt. It unfolded smoothly as densities changed. Expansion responded accordingly. Understanding radiation dominance explains why early structure formation was delayed. The universe needed time to cool and thin before gravity could sculpt it effectively. Radiation dominance also left observable traces. The cosmic microwave background reflects conditions from near the end of this era. As radiation gradually ceded control, matter became the primary driver of structure. And within this evolving balance, the universe continued expanding, preparing itself for the long era of galaxy formation that would follow. As expansion continued, the universe cooled and thinned. Radiation energy density decreased rapidly, while matter density fell more slowly. Eventually, matter overtook radiation as the dominant influence on expansion. This transition marked a significant change in cosmic behavior. Once matter dominated, gravity became more effective at gathering material into structures. Small density fluctuations could grow without strong resistance. The timing of this transition was critical. If matter had dominated too early, structure might form too quickly and unevenly. If too late, expansion would dilute matter before gravity could act. The universe achieved a balanced timing. During matter dominance, expansion slowed further. Galaxies began forming along the cosmic web. Clusters grew, voids expanded. This era lasted billions of years and encompassed most of cosmic history. Stars formed, planets emerged, chemical complexity increased. The influence of radiation did not vanish completely. It remained present, but no longer controlled expansion. Observations of large-scale structure and cosmic background radiation confirm this sequence. Models accurately reproduce the transition and its consequences. Matter dominance allowed the universe to become richly structured. Gravity could finally sculpt the cosmos effectively. As expansion continued, matter shaped the universe's visible form. And within this long era, the foundations were laid for environments capable of supporting complexity, stability, and eventually, conscious observation of the expanding universe itself. The universe's expansion has not followed a single, unchanging rate. Its pace has shifted over time, responding to the dominant form of energy present during each era. During inflation, expansion was extraordinarily rapid. After inflation ended, expansion slowed dramatically. In the radiation-dominated era, expansion proceeded quickly but steadily. Later, during matter dominance, it slowed further. These changes were governed by well-defined physical laws. General relativity describes how energy content influences expansion. Different forms of energy affect space in different ways. For billions of years, expansion gradually decelerated under gravity's influence. Matter pulled inward, resisting growth. The universe expanded, but reluctantly. More recently, expansion began accelerating again. This shift signals the influence of dark energy, a mysterious component that now dominates cosmic dynamics. Understanding these changing rates helps reconstruct cosmic history. Expansion serves as a clock marking transitions between eras. The universe did not rush through its story. It adjusted pace as conditions evolved. Each phase prepared the next. Rapid inflation set initial conditions. Slower expansion allowed structure. Acceleration now shapes the future. As space continues to stretch, its pace reflects the universe's contents. Expansion is not just motion, it is a response, and through its changing rhythm, the universe quietly reveals the forces guiding its long unfolding journey. In the universe today, expansion is no longer slowing, it is accelerating. This acceleration is driven by an unknown influence called dark energy, which now dominates the universe's total energy content. Unlike matter or radiation, dark energy does not clump or dilute easily as space expands. Dark energy appears to be a property of space itself. As space grows, more dark energy seems to come into existence, gently pushing galaxies apart at an increasing rate. This effect becomes noticeable only on the largest scales, beyond galaxy clusters. For most of cosmic history, gravity slowed expansion. Matter pulled inward, resisting growth. But as space expanded and matter thinned, dark energy's influence gradually overtook gravity's restraint. This transition happened relatively recently in cosmic terms, billions of years after the Big Bang. Since then, expansion has accelerated steadily. Dark energy's nature remains unknown. It may be related to vacuum energy, new fields, or modifications of gravity. Experiments continue probing its behavior through observations of distant galaxies and supernovae. Despite uncertainty, dark energy fits consistently into cosmological models. Its effects are measured precisely, even if its origin is mysterious. As expansion accelerates, distant galaxies recede faster. The universe grows quieter and more isolated over time. And within this accelerated expansion, the long story begun at the Big Bang continues unfolding, guided now by a subtle force embedded within space itself. Although the universe expands on large scales, this expansion does not tear apart everything within it. Bound systems such as galaxies, solar systems, and atoms remain intact. Their internal forces easily overpower the gentle stretching of space. Expansion becomes significant only across vast, relatively empty distances between galaxy clusters. Within denser regions, gravity and electromagnetic forces dominate completely. This is why planets do not drift away from their stars, and why atoms do not slowly expand. Local structures are held together by forces much stronger than cosmic expansion. The distinction lies in scale. Expansion operates globally, shaping the universe's overall structure. Binding forces operate locally, maintaining stability within that structure. This separation allows the universe to grow without destroying what has formed. Space stretches between systems, not within them. Understanding this balance helps reconcile expansion with everyday experience. The universe can grow larger while remaining stable in familiar ways. Over time, expansion increases distances between distant galaxies. Locally, nothing changes. Life, planets, and stars continue unaffected. This calm coexistence reinforces the universe's gentle nature. Expansion is not a tearing force. It is a quiet stretching that respects existing bonds. As space continues to grow, it carries galaxies apart while preserving internal order, and within this expanding framework, structure endures, protected by the same physical laws that shaped it from the beginning. Because the universe has a finite age and light travels at a finite speed, there is a limit to what we can observe. The observable universe includes all regions from which light has had time to reach us since expansion began. This boundary is not an edge of the universe itself. It is a horizon defined by physics. Beyond it, space may continue indefinitely, but its light has not yet arrived. As time passes, this horizon expands. Light from increasingly distant regions slowly reaches us. The observable universe grows, revealing more of cosmic history. The most distant light we see today comes from the cosmic microwave background. It marks the earliest moment when light could travel freely. Earlier times remain hidden behind opacity. This limitation shapes our understanding. Cosmology works within observable bounds, inferring unseen regions through theory and consistency. The finite observable universe creates a layered view of time. Looking farther means looking earlier. Distance becomes history. Even with this limitation, patterns remain consistent. Observed regions reflect universal laws. There is no sign that physics changes beyond the horizon. This finite visibility encourages humility. We know much, yet not everything. As expansion continues, the observable universe slowly grows, revealing new regions while others drift beyond reach. And within this shifting horizon, we continue tracing the universe's story, aware that what we see is only part of a much larger, quietly expanding whole. As expansion accelerates, some distant galaxies will eventually move beyond our observable horizon. Their light, emitted in the future, will never reach us. Over time, these regions will fade from view, not because they disappear, but because space expands too quickly between us. This process has already begun. Extremely distant galaxies are receding so rapidly that their future light is effectively cut off. They exist, but they become unreachable. This does not affect nearby galaxies bound by gravity. Local groups remain visible and intact. The loss occurs only across immense cosmic distances. In the far future, observers may see a much emptier universe. Distant galaxies will redshift beyond detection. Only nearby structures will remain visible. This gradual isolation is a natural consequence of accelerated expansion. It unfolds slowly, without disruption. Despite this, the universe's history remains encoded in the light already received. Past expansion left traces that cannot be erased. This horizon does not signal an end. It reflects changing accessibility. Understanding this process reminds us that observation depends on timing. What is visible now may not be visible forever. As expansion continues accelerating, the universe grows quieter and more separated. Yet within this separation lies continuity. Space stretches, horizons shift, and the universe carries its story forward, even as parts of it gently slip beyond view. The Big Bang Theory explains how the universe evolved from an early hot, dense state into its current expanding form. It does not explain why the universe exists or what caused expansion to begin. These deeper questions remain open. Physics describes behavior within space-time. The Big Bang marks the beginning of that framework. Asking what caused it may require theories not yet developed. This distinction matters. The Big Bang is not a creation story in a philosophical sense. It is a model of change over time, grounded in observation and mathematics. Evidence supports this model strongly. Expansion, background radiation, and elemental abundances all align with its predictions. Yet the ultimate origin remains beyond current reach. Some theories suggest earlier phases, quantum origins, or cyclic models. These ideas are actively explored but remain unconfirmed. This uncertainty does not weaken the theory. It clarifies its scope. Science advances by explaining what can be tested. The universe does not demand final answers immediately. It reveals itself gradually. By focusing on evolution rather than origin, cosmology provides a coherent narrative without speculation beyond evidence. As expansion continues, new observations may extend understanding further back, or they may reveal limits that invite new frameworks. For now, the Big Bang offers a calm, consistent explanation of how the universe became what it is. And within that understanding, we can rest, knowing that mystery remains not as a flaw, but as an open space still expanding alongside everything else. The strength of the Big Bang Theory lies in the way independent observations converge on the same story. Expansion, background radiation, and elemental abundances all point toward a universe that began hot and dense, then cooled as space expanded. Galactic redshift reveals expansion directly. The cosmic microwave background preserves early conditions. Big Bang nucleosynthesis predicts elemental ratios observed today. Each line of evidence arises from different measurements, yet they agree. This convergence matters. A single observation can mislead. Multiple, unrelated confirmations build confidence. Together, they form a coherent framework that explains both large-scale structure and fine detail. Importantly, these observations were not designed to fit the theory after the fact. Many were predicted before being observed. The cosmic microwave background, for example, was anticipated decades before its accidental discovery. This predictive power distinguishes scientific theories from speculation. The Big Bang continues to generate testable predictions that observations repeatedly confirm. As instruments improve, evidence grows more precise rather than contradictory. Measurements refine parameters without overturning the model. This consistency suggests the universe follows reliable rules, even across extreme conditions. The Big Bang is not supported by belief, but by agreement between observation and theory. And as expansion continues, the universe quietly continues confirming the story written into its own light, structure, and motion. The Big Bang Theory did not appear fully formed. It developed gradually as observations improved and understanding deepened. Early versions focused primarily on expansion. Later refinements incorporated radiation, particle physics, and inflation. This evolution reflects scientific strength rather than weakness. As new evidence emerges, theories adapt. The core idea remains stable while details grow more precise. Inflation was added to address questions about uniformity and geometry. Dark matter and dark energy were introduced to explain observed motions and expansion behavior. Each addition responded to data, not preference. Despite these refinements, the theory's foundation remains intact. Expansion from a hot, dense state continues to explain observations consistently. This adaptability allows the theory to remain relevant. It absorbs new information without collapsing under contradiction. Importantly, earlier versions were not wrong. They were incomplete. Each revision expanded explanatory power. The Big Bang's growth mirrors the universe it describes. It unfolds gradually, becoming richer over time. Scientific understanding is never static. It deepens with patience and evidence. As expansion continues, new observations may further refine cosmology. The theory will evolve again. This openness ensures longevity. The Big Bang Theory remains not a fixed doctrine but a living framework, quietly adjusting as the universe reveals more of itself through careful observation and measured understanding. Because light takes time to travel, observing distant objects means seeing them as they were in the past. Telescopes therefore function as time machines, revealing earlier stages of the universe's evolution. When we observe nearby stars, we see them as they were years ago. Distant galaxies appear as they were billions of years in the past. Looking farther means looking earlier. Modern telescopes detect faint light stretched by expansion. This light carries information from young galaxies forming soon after the Big Bang. Infrared and microwave instruments extend vision further back. They capture radiation invisible to the eye, including the cosmic microwave background. Each improvement pushes the observational boundary deeper into cosmic history. The universe's timeline becomes more complete. This ability allows cosmologists to test theories directly. Predictions about early conditions can be compared with observation. Seeing back in time also reveals change. Galaxies evolve, structures grow, expansion alters appearance. The universe is not static when viewed this way. It is dynamic and layered. Time becomes visible across distance. Space becomes history. As telescopes grow more sensitive, they reveal fainter, older light, yet limits remain. Still, through observation, we trace the universe's story backward with increasing clarity. And with each glimpse into the past, expansion's quiet influence becomes more evident, linking distant light to the universe's earliest moments. By measuring expansion, scientists can estimate how long the universe has been growing. The rate at which galaxies recede allows calculation of the universe's age. This method relies on Hubble's constant and refined models accounting for changing expansion rates. When applied carefully, it yields a consistent result. Current measurements indicate the universe is about 13.8 billion years old. This value aligns with independent evidence from stellar evolution and background radiation. Stars in ancient clusters show ages slightly younger than the universe. As expected, the cosmic microwave background encodes conditions consistent with this timeline. Agreement across methods strengthens confidence. Different clocks point to the same age. This convergence suggests expansion has followed predictable rules throughout cosmic history. Age is not an abstract number. It represents the time available for structure to form, stars to evolve, and complexity to emerge. Knowing the universe's age provides context. It situates humanity within a vast timeline. The universe is old, but not infinitely so. Its history has length and direction. As measurements improve, age estimates become more precise, not contradictory. Through expansion, time becomes measurable. The universe leaves records of its duration in light, motion, and structure. And by reading these records, we quietly place ourselves within a long, unfolding story that began billions of years ago. The Big Bang was not a single moment locked in the past. It marked the beginning of a process that continues today. Expansion still shapes the universe. Structure still evolves. Conditions continue changing. Galaxies merge. Stars are born and die. Space stretches steadily. Nothing is frozen in place. Even the cosmic microwave background continues cooling. Expansion lengthens its wavelengths further, fading it gradually. Future changes will differ from the past. As dark energy dominates, expansion accelerates. Distant galaxies grow harder to observe. The universe becomes quieter, yet change never stops entirely. Local systems remain active. Stars continue shining. Matter continues cycling. The Big Bang describes a universe defined by evolution rather than stasis. It is a story still being written. Understanding this ongoing change shifts perspective. The universe is not complete. It is unfolding. Time, space, and matter remain connected through expansion. Each moment belongs to the same process that began billions of years ago. As we rest within this understanding, urgency fades. The universe moves at its own pace. Expansion continues calmly, without goal or destination. And within that calm, the universe carries forward everything it has become, gently evolving through space and time, still guided by the same quiet principles that shaped its earliest moments. The Big Bang did not produce galaxies, stars, or planets in its earliest moments. Instead, it created the conditions under which these structures could eventually form. Early expansion left the universe hot, smooth, and nearly uniform, with matter spread thinly across space. Galaxies required time. Gravity needed billions of years to gather diffuse gas into dense regions. Cooling had to proceed far enough for matter to remain bound. The Big Bang began this process, but did not complete it. This distinction is important. The Big Bang explains the universe's initial state and overall evolution, not the immediate appearance of complexity. Structure emerged gradually, guided by physical laws acting patiently over immense timescales. Early matter drifted through expanding space, influenced by tiny density variations. These variations grew slowly, eventually forming filaments, halos, and galaxies. The universe's earliest moments were simple. Complexity came later. Understanding this removes the idea of instant creation. The universe did not arrive fully formed. It unfolded. Expansion provided room. Gravity provided gathering. Time provided change. This slow progression mirrors many natural processes. Nothing rushed. Nothing forced. The Big Bang began a journey rather than concluding one, and as expansion continued, it allowed structure to arise step by step, transforming a nearly uniform beginning into the richly patterned cosmos we observe today. While expansion drives galaxies apart on the largest scales, gravity works locally to pull matter together. These two influences coexist without conflict, each dominating different regimes of space. In regions where matter density is high, gravity overwhelms expansion, gas clouds collapse, stars form, galaxies assemble. Expansion does not prevent these processes. It simply shapes the environment around them. This balance allows structure to persist. Without gravity, expansion would disperse matter too quickly. Without expansion, gravity would collapse everything into dense clusters. The universe maintains equilibrium between these forces. Gravity's influence grows stronger as matter gathers. Once bound, systems resist expansion entirely. Galaxies remain intact. Clusters remain cohesive. This interaction explains why the universe can expand while remaining richly structured. Expansion stretches the cosmic background. Gravity sculpts detail within it. Over time, gravity builds complexity from simplicity. It turns small variations into enduring structures. The universe's history reflects this partnership. Expansion set the scale. Gravity filled it. Neither force dominates completely. Each plays a role. Understanding this relationship reveals the universe's restraint. Growth occurs without destruction. Structure emerges without collapse. As expansion continues, gravity quietly maintains order within it, ensuring that while space grows ever larger, the structures formed within it remain stable, enduring, and deeply interconnected across cosmic time. The mathematical framework underlying the Big Bang theory comes from general relativity, Einstein's theory describing how space and time respond to energy and matter. When applied to the universe as a whole, these equations naturally predict expansion. Solutions to Einstein's equations show that a universe filled with matter cannot remain static. It must either expand or contract. This insight emerged even before observational evidence confirmed expansion. When expansion is traced backward using general relativity, it leads to a dense, hot state consistent with Big Bang predictions. This consistency ties cosmic history directly to fundamental physics. General relativity also explains how expansion rate changes over time. Different energy components influence how quickly space stretches. Radiation, matter, and dark energy each play roles. Importantly, general relativity does not describe the universe's earliest moment perfectly. At extreme densities, quantum effects become important. This signals limits of the theory, not its failure. Within its domain, general relativity remains remarkably accurate. Observations align closely with its predictions across cosmic scales. This alignment reinforces confidence in the Big Bang framework. Expansion is not an assumption. It arises naturally from tested equations. The universe follows coherent rules. Its behavior reflects underlying principles rather than arbitrary motion. Through general relativity, the Big Bang becomes not speculation but consequence. And within this consistent framework, expansion continues quietly, shaped by geometry, energy, and time itself. As expansion is traced back toward the universe's earliest moments, densities and energies rise dramatically. Under these conditions, quantum physics becomes essential for describing behavior. Classical physics alone is no longer sufficient. Particles behave differently at these scales. Fluctuations become significant. Space itself may exhibit quantum properties. Understanding this regime requires theories that unite gravity with quantum mechanics. Such a theory does not yet exist in complete form. Current models can describe early expansion only up to a point. Beyond that, predictions become uncertain. This limitation marks the boundary of knowledge rather than failure. It highlights where new understanding is needed. Quantum effects likely played a role in seeding structure. Tiny fluctuations arising from quantum uncertainty were stretched by expansion, leaving lasting imprints. The earliest universe may have been governed by probabilistic processes rather than deterministic ones. Outcomes were shaped by chance within physical constraints. This quantum beginning does not imply chaos. It follows statistical laws. Patterns emerge reliably when viewed across large scales. Modern observations support this connection. The structure of the universe reflects early quantum influences. As expansion carried the universe forward, quantum effects faded in prominence, replaced by classical behavior. Yet their imprint remains. And within this quiet transition from uncertainty to structure, the universe demonstrates how complexity can arise from fundamental randomness guided by consistent physical laws. One of the strongest qualities of the Big Bang model is its ability to make predictions that can be tested through observation. Long before certain evidence was found, the theory forecast phenomena later confirmed. It predicted expansion before redshift measurements were precise. It predicted background radiation before it was detected. It predicted elemental abundances before measurements confirmed them. This predictive success distinguishes the model from descriptive ideas. It does not merely fit known facts, it anticipates new ones. When predictions fail, models must change. When they succeed repeatedly, confidence grows. The Big Bang has passed these tests across decades of research. Each new observation refines parameters without overturning the core framework. This reliability suggests the model captures something fundamental about reality. It reflects how the universe actually behaves. Predictive power allows progress. Scientists design experiments knowing what signatures to look for. Observations become conversations with theory. As technology improves, predictions become more precise. Telescopes probe earlier times. Measurements sharpen. The Big Bang continues to guide inquiry. It frames questions and constrains answers. This guidance does not close inquiry, it opens it. Through prediction, the universe reveals itself gradually. Expansion leaves measurable traces. Light carries information. And through these signals, the Big Bang model continues quietly proving its value, connecting theory and observation across billions of years of cosmic evolution. Modern cosmology relies on precise measurement rather than broad observation. The Big Bang theory is continually tested by instruments capable of detecting subtle variations in light, motion, and structure across vast distances. Satellites measure the cosmic microwave background to extraordinary accuracy. They detect temperature differences smaller than 1 part in 100,000. These measurements reveal early conditions with remarkable clarity. Large surveys map galaxy distributions across billions of light years. Patterns match predictions derived from early fluctuations and expansion history. Small deviations refine models rather than undermine them. Precision also applies to elemental abundances. Ratios of hydrogen, helium, and lithium align closely with nucleosynthesis predictions. These measurements come from stars, gas clouds, and distant galaxies. Time itself is measured through cosmic clocks. Stellar ages, radioactive decay, and expansion rates converge on consistent timelines. This accumulation of precise agreement strengthens confidence. Independent measurements reinforce one another. Precision does not eliminate mystery. It narrows possibilities. It defines boundaries. As instruments improve, uncertainty shrinks. Predictions sharpen. Models adjust. The Big Bang remains testable because it produces measurable outcomes. Expansion leaves signatures. Early conditions imprint patterns. Through careful measurement, the universe speaks softly but clearly. And by listening closely, cosmology refines its understanding, tracing the universe's growth with increasing resolution across time, space, and the quietly expanding fabric that connects them. To understand how the universe evolved, scientists use computer simulations that model expansion, gravity, and matter interactions over billions of years. These simulations begin with conditions predicted by the Big Bang and follow structure formation forward in time. Starting from tiny fluctuations, simulated matter gathers into filaments, clusters, and voids. The resulting patterns closely resemble observed cosmic structures. This agreement provides strong validation. Simulations incorporate dark matter, ordinary matter, and expansion dynamics. They test how each component influences outcomes. Adjusting parameters reveals sensitivity and balance. These models do not create galaxies arbitrarily. They follow physical laws step by step. Gravity pulls, expansion stretches, cooling allows collapse. By comparing simulations with observation, scientists refine understanding. Discrepancies highlight where models need adjustment, Simulations also explore alternative scenarios. They test what would happen under different initial conditions. Many possibilities fail to match reality. The success of Big Bang-based simulations suggests the theory captures essential truth. The universe behaves as expected when its early conditions are modeled correctly. Simulations do not replace observation, they complement it. Together, they form a dialogue between theory and reality. As computing power grows, simulations become more detailed. They reveal structure forming naturally from simple beginnings. Through simulation, the universe's long evolution becomes visible in accelerated form, allowing us to watch billions of years unfold, guided by expansion, gravity, and the quiet rules established at the universe's beginning. Despite its immense size, the universe displays large-scale order. Galaxies follow patterns. Structures repeat. This organization arises naturally from Big Bang conditions combined with physical laws. Expansion set a uniform stage. Inflation smoothed extremes. Tiny fluctuations introduced variation. Gravity amplified those variations into structure. The result is neither chaos nor rigidity. It is patterned complexity. Filaments, clusters, and voids repeat across space, reflecting common origins. Large-scale order does not require design. It emerges from simple rules applied consistently. This principle appears throughout nature. The Big Bang provided initial simplicity. Complexity followed through interaction rather than instruction. Observations confirm this order. Galaxy surveys reveal repeating structures across enormous distances. Statistical properties match theoretical expectations. This consistency suggests the universe is governed by stable laws. Order is not imposed, it arises. Understanding this can be calming. The universe is not random noise. It has structure without intention. As expansion continues, this order persists. Patterns stretch but remain coherent. Even as galaxies drift apart, their distribution retains memory of early conditions. The Big Bang explains why the universe looks organized on the larger scales. It connects early smoothness with later pattern. Through expansion and gravity, order emerges quietly. And within this vast, structured cosmos, the same principles apply everywhere, guiding matter into forms that repeat gently across the expanding fabric of space. The Big Bang theory describes observed expansion and early conditions, but it does not claim exclusivity over all cosmic possibilities. Other models explore what may have preceded or surrounded the Big Bang framework. Some theories propose cyclic universes that expand and contract repeatedly. Others suggest a multiverse where many universes exist with different properties. Still others explore quantum origins without classical beginnings. These ideas are not replacements for the Big Bang. They attempt to extend understanding beyond its limits. The Big Bang remains valid within its tested domain. Science allows multiple models to coexist while evidence accumulates. Theories compete through prediction and observation, not preference. At present, no alternative model explains observed data better than the Big Bang. Expansion, background radiation, and structure formation remain best described by it. Exploring alternatives encourages deeper insight. It clarifies what is known and what remains uncertain. The Big Bang's openness to extension reflects scientific humility. It does not claim finality. Understanding grows incrementally. As observations improve, some models may gain support or fade. Until then, the Big Bang remains central. Its role is explanatory, not absolute. Within its scope, it offers clarity. Beyond it, questions remain open. This balance allows curiosity without confusion. And within the expanding universe, science continues exploring calmly, guided by evidence, aware that understanding evolves just as the cosmos itself continues to unfold. The Big Bang links all cosmic events through a shared origin in time. Every galaxy, star, planet, and atom traces its history back to the same early conditions. This connection is not symbolic, it is physical. Expansion carries matter apart, but history binds it together. Light, structure, and motion all originate from common beginnings. This shared timeline means distant galaxies are not separate stories. They are parallel chapters unfolding from the same starting point. Understanding this continuity reshapes perspective. The universe is not a collection of isolated events. It is a single process expressed across space. Time flows outward from the Big Bang, carrying everything with it. Past conditions influence present structure. Present conditions shape future outcomes. This connection persists despite distance. Space expands, but causality remains anchored in shared history. The cosmic microwave background records early conditions. Elemental abundances reflect early reactions. Structure traces early fluctuations. All evidence points back to the same origin. This unity does not imply uniformity. Diversity arises naturally, but diversity unfolds within a connected framework. The Big Bang offers coherence. It turns scattered observations into a unified narrative. Within this narrative, nothing stands alone. Every moment belongs to the same unfolding process. As expansion continues, the universe grows larger, but its history remains shared. And within that shared origin, we find not urgency, but continuity, linking every quiet moment now to the earliest unfolding of space and time itself. One of the most striking aspects of the Big Bang theory is how it connects the smallest scales of physics with the largest structures in the universe. Processes occurring at subatomic levels left imprints that later shaped galaxies spanning millions of light years. Quantum fluctuations, born at microscopic scales, were stretched by early expansion into patterns that guided matter's movement. These tiny variations became the seeds of cosmic structure, demonstrating a direct link between the very small and the very large. This connection means that understanding particles helps explain galaxies, and understanding galaxies informs particle physics. The universe does not separate scales, it integrates them. Experiments in particle accelerators probe energies similar to those present in the early universe. Observations of the cosmic microwave background test predictions from quantum theory. Together they form a continuous picture. This unity reduces complexity. Instead of separate explanations for different scales, a single framework applies broadly. The Big Bang does not belong solely to cosmology. It belongs equally to fundamental physics. This interconnectedness brings calm coherence. Nothing exists in isolation. Every scale influences others. As expansion carried the universe forward, early quantum behavior remained encoded in large-scale structure. The smallest uncertainties shaped the largest forms. Through this link, the universe reveals its continuity. And within that continuity, we see that from particles to galaxies, everything unfolds within the same expanding story, governed by shared principles quietly expressed across all scales of existence. The Big Bang theory does not predict the exact position of every galaxy. Instead, it predicts statistical patterns across large scales. These patterns describe how matter should be distributed overall rather than in detail. This approach reflects the universe's complexity. Individual outcomes vary, but collective behavior follows clear rules. Much like weather patterns differ daily, yet follow climate trends, cosmic structure follows predictable statistics. Measurements of galaxy clustering match these predictions closely. The spacing of filaments, sizes of voids, and distribution of clusters align with models derived from early fluctuations. The cosmic microwave background also exhibits statistical patterns. Its temperature variations follow precise distributions expected from inflationary models. These agreements suggest the universe's randomness operates within constraints. Chance exists, but it is structured. Statistical prediction allows testing without requiring exact replication. It focuses on probabilities rather than specifics. This approach fits the universe's calm nature. It does not demand perfection. It allows variation. As expansion continues, these statistical patterns persist. Structure evolves, but underlying distributions remain stable. The Big Bang's success lies partly in this flexibility. It captures essential behavior without overspecification. Through statistics, the universe becomes understandable without becoming rigid. And within these quiet patterns, we see how early conditions continue shaping matter's arrangement across the vast, expanding cosmos. Although the early universe was extremely hot and dense, it was also highly ordered. Matter and energy were distributed smoothly, with only tiny deviations from uniformity. This low level of disorder is central to understanding cosmic evolution. In thermodynamic terms, the early universe had low entropy. This may seem counterintuitive given its extreme conditions, yet order is defined not by temperature but by arrangement. This early order allowed entropy to increase over time. Structure formation, star birth, and chemical complexity all rely on this initial state. If the universe had begun in a highly disordered condition, organized structures could not emerge. The Big Bang provided a rare starting point where change could unfold productively. This order is visible in the cosmic microwave background's uniformity. Small fluctuations exist, but large-scale smoothness dominates. The reason for this low entropy beginning remains one of cosmology's deepest questions. It may relate to gravity's unique behavior. What matters is its consequence. Order allowed time's arrow to exist. It allowed evolution. As expansion carried the universe forward, entropy increased steadily. Order gave way to complexity rather than chaos. This progression underlies everything that followed. And within this quiet transition from simplicity to richness, the universe demonstrates how a calm, ordered beginning can give rise to the vast diversity observed across the expanding fabric of space. 200 words. The Big Bang provides a reference point for the direction of time. From its low entropy beginning, the universe has moved steadily toward higher entropy states. This progression defines what we experience as the flow of time. Time's arrow is not imposed externally. It arises naturally from the universe's initial conditions. As entropy increases, processes become irreversible. Causes precede effects. Memory becomes possible. This directionality shapes all experience. Stars burn fuel. Heat flows outward. Structures form and decay. These processes depend on time's asymmetry. Expansion supports this arrow. As space grows, energy spreads, differences diminish, entropy rises. The Big Bang therefore anchors temporal order. It provides the condition from which time gains meaning. Without this low entropy start, time would lack direction. Events would not organize coherently. This does not require conscious observation. Time's arrow operates regardless of awareness. As expansion continues, time continues flowing forward. The universe evolves consistently. Understanding time as emerging from physical conditions removes mystery. It grounds experience in cosmic history. The Big Bang did not merely begin space, it began time's structure. And within that structure, Every moment unfolds in sequence, carried forward by expansion and entropy, connecting present stillness to the earliest ordering of the universe itself. The Big Bang situates humanity within a vast, continuous timeline. Our existence is not separate from cosmic history. It is one expression of it. Atoms forming our bodies were shaped by early expansion, stellar processes, and long-term evolution. The conditions allowing life trace back to the universe's earliest moments. This perspective reduces isolation. Humanity is not an exception. It is part of a process billions of years in motion. The same laws governing galaxies govern biology. Chemistry follows physics. Life follows cosmic conditions. Understanding this connection can be grounding. It places personal experience within a larger context without diminishing it. Timescales differ, but continuity remains. The universe evolves slowly. Life emerges briefly. Both belong to the same story. The Big Bang does not center humanity. It contextualizes it. This framing encourages humility and calm. We are neither accidental nor central. We are emergent. As expansion continues, the universe carries forward conditions that once allowed life to appear. Whether life arises elsewhere remains unknown. What is clear is connection. Everything shares the same origin. Within this shared history, awareness emerges temporarily, observing the universe that made it possible. And in recognizing this placement, we find not urgency, but quiet belonging within the long, expanding story of the cosmos. The darkness of the night sky carries information about the universe's history. If the universe were eternal and unchanging, every line of sight would eventually end at a star, and the sky would glow uniformly bright. This expectation is known as Olber's paradox. The Big Bang resolves this paradox naturally. The universe has a finite age, so light from all stars has not had time to reach us. Many stars simply have not existed long enough for their light to arrive. Expansion adds another effect. As space stretches, light loses energy. Distant starlight becomes redshifted, fading beyond visible wavelengths. Even light that does reach us arrives weakened. Together, finite age and expansion keep the sky dark. The universe is young enough and stretching enough to prevent overwhelming brightness. This explanation connects everyday experience to cosmic history. Darkness is not absence, it is information. The night sky reflects limits imposed by time and expansion. As the universe continues expanding, distant light will fade further. Darkness will deepen. Yet within that darkness, stars continue shining locally. Structure persists. Understanding this removes mystery without removing wonder. The dark sky becomes a quiet reminder of the universe's unfolding. The Big Bang does not just explain origins, it explains what we see now. And within the calm darkness overhead, we glimpse the combined effects of expansion, time, and the universe's gentle restraint. Just as the universe cooled in the past, it will continue cooling in the future. Expansion spreads energy across ever-growing space, lowering temperature steadily over time. This process has no known endpoint. Stars will eventually exhaust their fuel. New star formation will slow as gas becomes scarce. The universe will grow darker and colder. Radiation will continue stretching into longer wavelengths. The cosmic microwave background will fade further, approaching absolute zero. This cooling does not imply sudden collapse or destruction. It unfolds gradually across timescales far beyond imagination. The Big Bang framework allows scientists to project these trends forward. Expansion defines the universe's long-term direction. Different models predict variations in detail, but cooling is consistent across them. This future is not empty. Local systems remain active for long periods. Stars burn for trillions of years. Black holes persist longer still. Cooling reshapes the universe slowly. Change continues, but at a gentler pace. Understanding this future can feel sobering, yet also calming. Nothing rushes. The universe moves steadily toward lower energy states, following the same rules that governed its past. From hot beginnings to cooler futures, the Big Bang describes a universe that changes predictably, and within that long cooling arc, each present moment remains part of a continuous, quietly expanding story. The Big Bang does not place the universe's origin at a specific point in space. There is no central location from which everything expanded outward. Expansion occurred everywhere simultaneously. This means no galaxy occupies a privileged position. From any location, the universe appears to expand uniformly. Observations look similar in all directions. This property reflects the nature of space itself. Space expands, carrying matter along. There is no external reference point. Imagining a center often comes from visualizing explosions. But the Big Bang was not an explosion within space. It was an expansion of space. Removing the idea of a center simplifies understanding. The universe does not revolve around a place. This structure aligns with observations. No preferred direction or location has been found. The absence of a center reinforces cosmic equality. Every region follows the same laws. Every observer sees similar patterns on large scales. This can feel disorienting at first, but it also removes hierarchy. The universe does not elevate any position. As expansion continues, this symmetry remains. Space stretches uniformly. Understanding a centerless universe encourages calm perspective. Nothing is singled out. The Big Bang began everywhere, and as space continues expanding everywhere, the universe unfolds evenly, without focal point or edge, guided quietly by the same physical principles across all locations and times. The Big Bang theory does not merely describe that the universe is expanding, it explains why expansion is expected. According to general relativity, a universe filled with matter and energy cannot remain static. Once expansion began, it continued naturally. Space responds to energy content, stretching under its influence. The Big Bang describes the universe starting from conditions that made expansion unavoidable. This does not require ongoing force. Expansion follows from initial conditions and physical laws. Observations confirm this behavior. Galaxies recede predictably. Background radiation stretches consistently. Expansion is not an anomaly. It is the universe's natural response. Even changes in expansion rate follow explanation. Radiation slowed expansion. Matter slowed it further. Dark energy now accelerates it. Each phase arises from the same framework. This continuity gives expansion coherence. It is not random motion. It is lawful evolution. Understanding this removes the need for constant intervention. The universe does not need pushing. It unfolds. The Big Bang provides the starting conditions. Physics provides the rules. Together, they produce a universe that grows, cools, and structures itself over time. As expansion continues, it remains governed by the same principles. The universe expands because it began expanding under conditions that made doing so inevitable. And within that inevitability, its evolution proceeds calmly, steadily, and predictably across the vast stretches of space and time. The Big Bang is often imagined as a momentary event. In reality, it is a framework describing an extended process. It encompasses expansion, cooling, structure formation, and ongoing change. There was no single instant that completed the universe. Instead, the universe emerged through stages, each building upon the last. The Big Bang includes inflation, nucleosynthesis, recombination and expansion across billions of years. It is a continuous story rather than a flash. Viewing it this way removes pressure to identify a precise beginning. The theory describes behavior across time, not a solitary act. This framework integrates observation and theory. It links early conditions with present structure and future evolution. Its strength lies in scope. It explains multiple phenomena within a single model. The Big Bang does not end. Expansion continues. The framework remains active. Understanding this allows flexibility. New discoveries refine details without dismantling the whole. The universe remains dynamic within this structure. Thinking of the Big Bang as a framework aligns with its calm nature. It is not explosive, it is developmental. From dense beginnings to expanding present, the universe unfolds within this model steadily. And as space continues stretching, the Big Bang remains relevant, not as a past event alone, but as the ongoing description of how the universe changes, grows, and gently carries its history forward. One of the Big Bang theory's quiet strengths is that it explains observations spanning vastly different eras of cosmic time. From the earliest detectable light to the present distribution of galaxies, the same framework remains consistent. The cosmic microwave background reflects conditions when the universe was young. Galaxy surveys show how structure evolved billions of years later. Measurements today reveal ongoing expansion. Each era fits into a continuous sequence. This temporal consistency matters. A theory explaining only one moment would be fragile. The Big Bang connects early simplicity to later complexity without contradiction. As time advances, predictions remain accurate. Expansion follows expected patterns. Structures grow as models suggest. No era stands apart. This continuity suggests the universe evolves coherently rather than episodically. Change follows rules that persist across time. Observations do not require resetting assumptions for different periods. The same physical principles apply. This stability brings calm to understanding. The universe is not reinventing itself at each stage. It unfolds. The Big Bang therefore functions as a temporal bridge. It links moments separated by billions of years into a single narrative. As expansion continues, future observations will extend this sequence further. Each new era adds detail without breaking continuity. Through this consistency across time, the Big Bang offers not just explanation but reassurance. The universe changes, but it does so predictably, guided by enduring laws that connect its earliest light to its present form within the same expanding story. Temperature throughout the universe follows a clear pattern predicted by the Big Bang. The farther back in time we observe, the hotter conditions appear. This gradient reflects continuous cooling driven by expansion. Early light shows higher temperatures. The cosmic microwave background was once much warmer. Today, it measures just a few degrees above absolute zero. This cooling trend is not arbitrary. Expansion stretches wavelengths, reducing energy. Space grows, heat disperses. By measuring temperature at different distances, scientists reconstruct this cooling history. Observations align closely with theoretical predictions. This agreement strengthens confidence. Independent measurements converge on the same thermal evolution. Temperature trends also influence structure. Hotter conditions prevent matter from clumping. Cooling allows gravity to act. Thus, temperature is not merely descriptive. It shapes cosmic behavior. The universe's thermal history unfolds gradually. There are no abrupt drops. Cooling follows predictable curves. This regularity reinforces the Big Bang's explanatory power. Temperature becomes a record of expansion. Even now, cooling continues quietly. Space stretches. Radiation thins. Understanding this pattern allows us to place the present within a long continuum. Today's cool universe is a late stage of a much hotter past. And as expansion continues, temperature will fall further, carrying the universe steadily toward quieter conditions, guided by the same calm physical processes that began with its earliest unfolding. The Big Bang Theory does not only explain that structures exist, it explains how they grow. From early density fluctuations to modern galaxies, structure formation follows a clear progression. Small differences in density grew under gravity's influence. Expansion slowed collapse but did not prevent it. Over time, matter gathered into increasingly complex forms. This growth was hierarchical. Small structures formed first, larger ones assembled later through mergers and accretion. Observations confirm this sequence. Young galaxies appear smaller and less organized. Older galaxies show mature structure. Simulations based on Big Bang conditions reproduce this growth accurately. When initial parameters match early observations, later structure emerges naturally. This predictive success shows continuity between early conditions and present complexity. Structure does not appear suddenly. It matures. This slow growth aligns with the universe's overall temperament. Change unfolds gradually, without urgency. Expansion provides scale. Gravity provides connection. Together, they guide structure forward. Understanding this growth helps explain why the universe looks the way it does today. Galaxies are neither random nor static. They are outcomes of long processes. As expansion continues, structure will keep evolving. Growth will slow, but it will not stop entirely. Within this ongoing development, the Big Bang remains a guide, explaining not just beginnings, but the patient shaping of form across cosmic time. When telescopes observe the deepest regions of space, they are also observing deep time. These views provide powerful tests of the Big Bang Theory. Distant galaxies appear younger, smaller, and more irregular. Star formation rates change with distance. Chemical composition varies predictably. These patterns match expectations from an evolving universe. Early galaxies differ from modern ones because conditions were different. The Big Bang framework anticipates these differences. It predicts gradual enrichment, growth, and organization. No abrupt inconsistencies appear. Observations fit smoothly into a developmental sequence. Deep field images reveal thousands of galaxies at various stages. Together, they form a timeline rather than a random collection. This alignment between observation and theory reinforces coherence. The universe behaves as predicted when viewed across distance and time. Expansion explains why distant objects appear fainter and redshifted. Early conditions explain their youthful features. Each deep observation adds confidence. The universe does not contradict its own history. As telescopes improve, they extend vision further back, yet the same patterns persist. This continuity suggests the Big Bang captures essential truth. By looking outward, we look backward. And with each glance, the universe quietly confirms the story of expansion, cooling, and gradual structure encoded in its earliest moments and carried forward across the vast reaches of space. At its core, the Big Bang presents the universe not as a finished object, but as an ongoing process. Everything observed is part of continuous change unfolding over time. Space expands, matter reorganizes, energy redistributes. Nothing stands still. This process-oriented view replaces static imagery with motion. The universe is becoming, not being. Such framing aligns with observation. Structures evolve, conditions shift, expansion persists. The Big Bang does not describe a completed past. It describes an active present shaped by earlier conditions. This perspective encourages patience. Understanding does not require finality. It requires continuity. The universe is not rushing toward an endpoint. It is following trajectories set long ago. Seeing the cosmos as process rather than event softens urgency. It invites quiet attention. Every moment belongs to the same unfolding. From early heat to present calm, change follows rules. The Big Bang organizes this change into a coherent framework. It connects past, present, and future without abrupt breaks. Within this view, the universe feels less explosive and more fluid. As expansion continues, the process continues. Nothing needs to be resolved immediately. The universe moves at its own pace, and within that pace, the Big Bang remains not a distant occurrence, but the ongoing description of how everything transforms gently over time, carrying history forward without interruption or haste. One of the Big Bang theory's quiet achievements is that it renders the universe understandable. It provides a framework where observations relate to one another rather than standing alone. Expansion, light, structure, and time connect coherently. Without such a framework, cosmic observations would remain isolated facts. With it, they form a narrative shaped by physical law. The Big Bang does not simplify the universe by removing complexity. It organizes complexity, showing how diverse phenomena emerge from shared beginnings. This coherence reduces confusion. Galaxies, radiation, and motion no longer compete for explanation. They support one another. Understanding does not require knowing everything. It requires knowing how pieces fit together. The Big Bang offers that fit. It explains why distant light is redshifted, why background radiation exists, why structure appears patterned rather than random. This understanding is cumulative. Each new observation integrates smoothly. The universe becomes legible, not solved. Such legibility invites calm curiosity rather than urgency. There is time to learn. The story unfolds slowly. As expansion continues, new data will refine understanding. The framework remains flexible. This openness keeps inquiry alive without instability. The Big Bang does not close questions. It orders them, and within that order, the universe becomes something we can quietly contemplate, not as an unsolvable mystery, but as a process whose behavior, though vast, follows patterns we can patiently trace across space and time. In cosmology, theory and observation depend deeply on one another. The Big Bang stands where these two meet. It translates abstract equations into observable consequences. Mathematics predicts expansion. Telescopes measure it. Theory forecasts background radiation. Instruments detect it. This dialogue strengthens both sides. Theory guides observation. Observation refines theory. The Big Bang framework is not built on speculation alone. It is built on repeated alignment between expectation and measurement. When discrepancies arise, they do not break the framework, they sharpen it. Parameters adjust. Understanding improves. This partnership prevents drift. Theory remains grounded. Observation remains interpretable. The universe does not reveal itself all at once. It offers fragments. The Big Bang assembles them. This assembly is not forced. It respects uncertainty. It allows margins. Through this balance, cosmology remains stable yet responsive. Understanding grows through patience rather than leaps. As expansion continues, observations will extend further. Theory will adapt accordingly. This unification creates confidence without finality. Knowledge remains provisional, yet reliable. The Big Bang exemplifies this scientific temperament. It does not claim certainty beyond evidence. It does not retreat from test. And within this steady exchange between idea and observation, the universe becomes knowable in layers, revealing its history through light, motion, and structure, all interpreted through a framework that remains calm, coherent, and open to refinement. By tracing expansion backward, the Big Bang theory points toward a time when the universe was smaller, denser, and hotter than at any later stage. This trajectory suggests a beginning to the universe's current phase. This beginning is not described as a moment of creation in the everyday sense. It marks the start of expansion and the emergence of space-time as we understand it. The evidence for this beginning comes from consistent observation. Expansion, background radiation, and thermal history all converge. This does not answer why the universe began. It describes that it did. Such distinction matters. Science identifies boundaries of explanation honestly. The idea of a beginning can feel unsettling, yet it also provides structure. History gains direction. Time acquires depth. The universe is not infinite in its past within this model. It has a measurable age. This finite history makes change meaningful. It allows evolution. A beginning does not imply fragility, it implies sequence. As expansion continues, the universe moves further from its early state, carrying memory forward. Whether this beginning is absolute or part of a larger context remains unknown. For now, the Big Bang describes the earliest accessible chapter. Within that chapter, we find not violence, but density and heat giving way to expansion. And in recognizing a beginning, we are reminded that the universe's story is one of unfolding, where time itself emerged gently and has been flowing steadily ever since. Despite its explanatory reach, the Big Bang does not resolve every question. It leaves room for mystery, especially at the earliest moments where current physics reaches its limits. What caused expansion to begin remains unknown. What preceded it, if anything, is unclear. These questions persist without contradiction. This openness is not a weakness. It reflects honesty about what can be known. The Big Bang explains observable evolution. It does not speculate beyond evidence. By doing so, it preserves space for future discovery. New theories may emerge. New observations may extend understanding. Mystery coexists with clarity. Some aspects are well described, others remain open. This balance keeps cosmology dynamic rather than dogmatic. The universe does not demand immediate answers. It allows gradual insight. Mystery invites patience. It encourages humility. As expansion continues, new signals may appear, or boundaries may remain. Either outcome is acceptable within scientific inquiry. The Big Bang provides a stable foundation from which questions can be asked carefully. It does not rush closure. Within this framework, wonder remains intact without confusion. The universe can be known partially and still inspire awe. And in this quiet coexistence of knowledge and mystery, the Big Bang offers not finality, but an invitation to continue observing, listening, and allowing the universe to reveal itself slowly, without pressure, across the widening canvas of space and time. The Big Bang unites all cosmic structures within a single shared history. Every galaxy, every star, every particle participates in the same unfolding timeline. Differences in location do not imply different origins. Expansion separates regions, but history connects them. This shared past explains why physical laws appear consistent everywhere. The universe developed together. Observations confirm this unity. Distant galaxies follow the same principles. background radiation surrounds all directions equally. The universe does not fragment into unrelated regions. It expands coherently. This coherence fosters continuity. Events billions of years apart remain linked by origin. The Big Bang transforms the universe from a collection of objects into a single evolving system. Within this system, change propagates forward. Early conditions shape later outcomes. Understanding this shared history softens isolation. Everything belongs. Space grows larger, yet connection persists through time. This perspective encourages calm integration. Nothing exists outside the story. As expansion continues, history accumulates. The universe becomes richer, not disconnected. Each moment adds to the same narrative. The Big Bang provides the opening chapter of this narrative, not to emphasize distance, but connection. And within this shared origin, we find that even as the universe expands endlessly outward, it remains inwardly unified by a common beginning, a common evolution, and a continuous, gently unfolding flow of time. The Big Bang does not claim to explain everything about the universe. It explains how observable conditions evolved from an early hot, dense state, not the ultimate reason those conditions existed. This distinction keeps the theory focused and reliable. By limiting its scope, the Big Bang avoids speculation beyond evidence. It describes expansion, cooling, and structure formation using measurable data. Questions of ultimate cause remain open. This boundary protects clarity. It prevents cosmology from becoming philosophy while still allowing philosophical reflection. The universe reveals what can be tested. The Big Bang responds only to that revelation. This restraint is a strength. It allows confidence without overreach. As observations improve, the theory expands carefully. New details integrate without rewriting foundations. Unanswered questions do not weaken what is known. They mark edges of understanding. Within those edges, explanation remains solid. The Big Bang therefore functions as a reliable map, not a complete territory. It guides exploration while acknowledging distance still unexplored. As expansion continues, evidence accumulates slowly. Understanding grows without urgency. And within this disciplined approach, the universe becomes steadily more comprehensible, not through claiming final answers, but through carefully explaining what observation allows and patiently leaving the rest for future insight. Although the Big Bang describes early conditions well, the very first moments remain hidden. At extreme densities and energies, known physical theories lose precision, signaling a boundary to present understanding. General relativity describes expansion accurately after the earliest instance. Quantum physics governs the smallest scales. Where these two meet, predictions become uncertain. This uncertainty does not imply disorder. It marks the edge of what current theories can describe. Physicists continue searching for a framework that unites gravity with quantum behavior. Such a theory would clarify the universe's earliest phase. Until then, the Big Bang begins just after that boundary. This honesty preserves reliability. It prevents false certainty. The universe does not reveal everything at once. Observations still reach extraordinary depth. Background radiation, particle behavior, and structure provide strong evidence for what followed. Yet the first fraction of a second remains indirect. This limitation does not weaken the story. It frames it. What comes after that boundary unfolds clearly. Expansion, cooling, and structure follow consistent patterns. The unknown beginning does not disrupt later understanding. Instead, it creates a horizon of inquiry. As expansion continues, new tools may approach this boundary more closely. For now, uncertainty rests quietly at the beginning, reminding us that understanding grows in stages. unfolding as patiently as the universe itself. The Big Bang theory is not closed to future discovery. It is structured to accommodate new information without collapsing under revision. This openness is essential to its durability. As new observations emerge, the theory adapts, parameters refine, details sharpen. The underlying framework remains stable. This flexibility allows integration of unexpected findings. Dark energy, for example, altered understanding of expansion without negating earlier results. The Big Bang does not resist refinement, it invites it. Future discoveries may illuminate inflation, dark matter, or quantum gravity. Each would extend the theory's reach. Compatibility does not mean uncertainty, it means resilience. A theory that cannot adapt fails quickly. One that adapts thoughtfully endures. The Big Bang has endured precisely because it evolves with evidence. This quality mirrors the universe itself. Change unfolds within continuity. As expansion continues, the universe will reveal more of its history. The theory will adjust accordingly. This process does not rush. It proceeds carefully. Understanding deepens through patience. The Big Bang provides a foundation sturdy enough to support growth. It does not demand final answers. Instead, it allows knowledge to accumulate gradually. Within this openness, science remains calm and grounded. And as discovery continues, the Big Bang remains a living framework, capable of growing alongside the universe it describes, without losing coherence or clarity. The Big Bang does more than describe the past. It provides context for the future. By understanding expansion and energy balance, scientists can project long-term trends. The universe began hot and dense. It cooled as space expanded. This pattern continues forward. Future conditions follow from present dynamics. Expansion accelerates, matter thins, energy disperses. The Big Bang links these phases into a single arc. This continuity offers perspective. The universe is not drifting randomly. It follows trajectories shaped early. Understanding this arc removes urgency. Change unfolds over immense timescales. The future is not abrupt. It is gradual. Cooling continues. Structures persist locally. Large-scale isolation increases. These outcomes reflect the same principles that governed early evolution. The Big Bang therefore frames time symmetrically. It connects beginnings with outcomes. Past and future are not separate stories. They are connected chapters. This framing supports calm reflection. Nothing suddenly ends. Nothing rushes. The universe moves steadily forward. As expansion carries space outward, history accumulates. The Big Bang anchors this accumulation, providing a reference for what has been and what may come. Within this long arc, every present moment is transitional, and in seeing the universe this way, we find continuity rather than finality, guided by the same gentle processes across time. Among all proposed cosmological models, the Big Bang remains the most consistent with observation. It explains expansion, background radiation, and structure formation within a single coherent framework. No alternative model matches this breadth with equal precision. This does not imply permanence, it reflects current evidence. Science proceeds by choosing the best explanation available while remaining open to improvement. The Big Bang earns its position through repeated testing. Predictions align with data. Measurements confirm expectations. Its success does not rest on belief, but on consistency. Where uncertainties exist, they are acknowledged. Where evidence is strong, confidence follows. This balance sustains reliability. The universe behaves as the theory predicts across scales and eras. That agreement matters. The Big Bang does not explain everything, but it explains enough to unify observation meaningfully. Until evidence suggests otherwise, it remains central. This position is not authority, it is earned. As new observations arrive, the theory will be tested again. If needed, it will adapt. For now, it stands as the clearest account of cosmic evolution, and within that clarity we can rest quietly, knowing that our understanding of the universe is not complete, but it is coherent, grounded, and sufficient to trace the long unfolding of space, time, and structure from its earliest known state. Despite the universe's immense complexity today, the Big Bang reveals that its beginnings were remarkably simple. Early conditions required only a few fundamental ingredients: energy, expansion, and physical law. From these, everything else emerged. There were no galaxies, no chemistry, no structure, only heat, density, and motion. This simplicity allowed evolution to proceed coherently rather than chaotically. Simple beginnings do not limit outcomes, they enable them. When rules are consistent, complexity can arise naturally through interaction and time. The universe did not need intricate initial design, it needed balance. This simplicity is reflected in early observations. The cosmic microwave background shows smoothness with minimal variation. Elemental abundances are uncomplicated. From this restrained start, diversity grew. This progression mirrors many natural systems. Complexity often arises from simple rules applied repeatedly. The Big Bang demonstrates this principle on the largest possible scale. Understanding this can be calming. The universe did not begin tangled, it began clear. As expansion continued, interactions layered complexity slowly. Nothing rushed. This simplicity remains encoded beneath modern structure. Patterns trace back to early uniformity. The universe still follows the same rules it began with. By recognizing this, we see that complexity is not overwhelming. It is cumulative. And beneath the richness of the cosmos lies a quiet, simple origin, steadily unfolding into the intricate universe we now observe. The Big Bang frames change not as disruption, but as the universe's normal state. From the beginning, everything has been in motion. Expansion, cooling, and structure formation are expressions of continuous change. Nothing in the universe was meant to remain fixed. Stability exists locally, but globally, evolution persists. This perspective reframes uncertainty. Change is not failure, it is process. Early simplicity changed into structure. Structure continues changing into new forms. Stars form and fade, galaxies merge, conditions shift. The Big Bang does not describe a universe that fell from perfection. It describes one that grows. This growth follows rules. It is not random, it is guided. Understanding this helps soften resistance to change. The universe does not cling to states, it moves through them. Expansion ensures that no moment lasts forever. Cooling ensures progression. Change is not something added later. It was present from the first expansion. This continuity brings reassurance. The universe is not unstable, it is evolving. As expansion continues, future conditions will differ from present ones. This is expected. The Big Bang prepares us for impermanence without chaos. Within this understanding, change becomes less alarming. It becomes rhythm. The universe changes because that is what it has always done. And within that ongoing change, there is consistency, order, and a quiet sense of direction unfolding across time. The Big Bang teaches not only what can be known, but what cannot yet be known. It defines boundaries of observation and theory, reminding us that understanding has edges. Some regions lie beyond the observable horizon. Some moments lie beyond theoretical reach. These limits are not failures. They are features of a universe governed by physical law. Light travels at finite speed. Expansion restricts access. Quantum behavior complicates early conditions. Within these constraints, cosmology operates carefully. The Big Bang does not promise total explanation. It promises reliable explanation within bounds. This honesty protects clarity. It prevents overstatement. Knowing limits allows focus. It directs inquiry where progress is possible. The universe does not reveal everything at once. It reveals in layers. This layered revelation encourages patience. Limits also preserve wonder. Not everything is resolved. Not everything is settled. Mystery remains without undermining understanding. As expansion continues, some limits may shift, others may remain. Either outcome is acceptable. The Big Bang framework respects these boundaries. It does not claim authority beyond evidence. This restraint is stabilizing. It reminds us that knowledge grows gradually, like the universe itself. Within known regions, understanding is strong. Beyond them, curiosity waits quietly. And in accepting limits, we find not frustration, but calm respect for a universe that reveals itself slowly, without obligation to hurry. Although the Big Bang describes immense motion and energy, it also invites stillness. Its story unfolds across billions of years, dwarfing urgency and compressing concern. Expansion happens quietly, cooling happens patiently, structure forms without haste. Nothing rushes. This perspective allows science to feel less demanding and more contemplative. Understanding does not require constant attention. It accumulates gently. The universe does not insist on being watched. It continues regardless. This scale encourages calm reflection. Personal moments become small but not insignificant. We are brief participants within a long unfolding. The Big Bang connects our present stillness to ancient motion. The same expansion shaping galaxies carries this moment forward. This continuity softens separation. We are not outside the universe's process. We are within it. Science here becomes grounding rather than stimulating. It reassures through consistency. The universe behaves predictably across time. That reliability invites rest. Understanding does not require action. It requires awareness. The Big Bang story does not demand urgency or resolution. It allows space for quiet attention. In this way, cosmology becomes meditative. Motion exists, but pace is slow. And within that slow unfolding, we find permission to be still, knowing that even in rest, we remain part of a universe calmly expanding, steadily changing, without need for intervention or concern. The Big Bang is not over. It did not finish long ago. It continues as expansion, as cooling, as gentle change moving forward through time. The universe is still unfolding. Nothing needs to be completed tonight. The cosmos does not rush. It expands calmly, carrying everything with it. From dense beginnings to quiet present, the universe has moved patiently. That patience remains. Every star, every atom, every breath exists within this ongoing expansion. You do not need to hold the details. The universe holds them already. Understanding can soften into acceptance. Knowledge can ease into rest. The Big Bang does not demand attention now. Its work continues without effort. Space stretches. Time flows. Change proceeds gently. You are part of this motion, but you are not responsible for it. For now, there is nothing to solve, nothing to remember. The universe will keep expanding whether you watch or sleep. Its earliest moments are far behind. Its future stretches quietly ahead. Between those vast spans lies this moment. Let your thoughts slow. Let awareness dim. Just as the universe cooled from intense beginnings, the mind can cool too. Everything is in motion, yet everything is okay. Thank you for spending this time here, drifting through cosmic history. For now, allow yourself to rest. Good night.